The detection of exoplanets has evolved remarkably since the initial confirmed discovery in the mid-1990s. Astronomers now utilize an array of sophisticated methods to find planets outside our solar system, each presenting its own unique advantages and obstacles. One of the most prominent techniques, the transit method, involves monitoring the brightness of stars over time. This approach seeks out small periodic dips in starlight that signal a planet passing in front of its star, momentarily blocking a fraction of its light. This not only confirms a planet's existence, but also yields information about its size and, in some instances, its atmospheric composition. Another widely used technique is the radial velocity method, also known as the Doppler method, which measures a star's slight wobble caused by the gravitational pull of an orbiting planet. This wobble can reveal the planet's mass, and while it doesn't directly observe the planet, it provides essential data about its characteristics. As technology progresses, astronomers are leveraging space telescopes like the Kepler Space Telescope and the Transiting Exoplanet Survey satellite, or TESS, which have significantly enhanced our ability to detect exoplanets. By continuously monitoring vast sections of the sky for transits, these instruments have expanded our cosmic census. The advent of direct imaging has also been revolutionary, enabling scientists to capture actual pictures of exoplanets by blocking out the overwhelming light of their host stars. This makes it possible to study their atmospheres and even search for signs of life, though this method remains challenging due to the extreme brightness contrast between stars and their planets. Additionally, gravitational microlensing has emerged as a fascinating technique relying on the bending of light caused by the gravitational field of a massive object like a star. This allows astronomers to detect planets that might otherwise be too faint or distant to see. With the development of innovative technologies such as high-resolution spectrographs that can analyze the light from distant stars, researchers can now identify the chemical compositions of exoplanet atmospheres. They search for elements associated with life like oxygen and methane, which could indicate biological activity. The James Webb Space Telescope is expected to provide unprecedented insights into exoplanet atmospheres, potentially revealing whether they possess conditions suitable for life. Meanwhile, machine learning is playing a pivotal role in analyzing vast amounts of data from multiple sources, helping to identify potential exoplanets more efficiently than ever before. Each of these methods brings us closer to understanding the diverse worlds that exist beyond our solar system. With thousands of confirmed exoplanets ranging from gas giants to rocky planets, and many more waiting to be discovered, we are continually refining our understanding of the cosmos. Exoplanets, also known as extrasolar planets, are planets that exist outside our solar system, orbiting stars other than our Sun. The discovery of these celestial bodies has transformed our understanding of the universe, revealing that planets are not unique to our solar system, but are common throughout our galaxy, the Milky Way. As of now, thousands of exoplanets have been confirmed, with many more candidates awaiting further verification. This burgeoning field of research is significant for several reasons, one of which is the potential for finding life beyond Earth. By studying the atmosphere's compositions and orbits of these distant worlds, astronomers can identify which exoplanets may be located within the habitable zone of their respective stars, the region where conditions might be right for liquid water to exist, a key ingredient for life. Moreover, exoplanets provide valuable clues about how planetary systems form and evolve. By analyzing their sizes, masses, and distances from their stars, researchers can develop models that explain the processes that lead to planet formation, including the role of dust and gas in protoplanetary disks. This understanding not only helps us learn about our own solar system's history, but also contributes to our knowledge of other solar systems, which may vary greatly from our own. Additionally, the study of exoplanets pushes the boundaries of our technology and observational capabilities. For instance, missions like the Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, or TESS, have employed innovative techniques such as the transit method, which detects dips in starlight caused by an exoplanet passing in front of its star, revealing its size. Furthermore, the significance of exoplanets extends to their diversity, as they come in a remarkable variety of sizes and compositions, from gas giants much larger than Jupiter to rocky planets similar to Earth. This diversity challenges our previous notions about planet formation and fosters a broader understanding of what types of worlds exist in the universe. Exoplanets also serve as a testing ground for theories related to planetary atmospheres, climate, and potential habitability, as researchers examine the conditions on these distant worlds, looking for signs of water vapor, carbon dioxide, and other molecules that could indicate the presence of an atmosphere conducive to life. The significance of exoplanets in astronomical research is also underscored by their potential to answer fundamental questions about our place in the universe as we continue to discover more. The first confirmed detection of an exoplanet occurred in 1992, specifically around a pulsar known as PSR B257+12, which is located approximately 2,000 light-years away in the constellation Virgo. This groundbreaking discovery was made by astronomers Alexander Wolszczan and Dale Frail, who used the method of pulsar timing to identify the presence of planets orbiting this pulsar. Pulsars are highly magnetized rotating neutron stars that emit beams of electromagnetic radiation, and as these beams sweep past Earth, they can be detected as regular pulses of radio waves. By precisely measuring the timing of these pulses, Wolszczan and Frail were able to observe slight variations in the timing caused by the gravitational influence of orbiting planets, which indicated that at least 2 planets were in orbit around PSR B257+12. This detection was revolutionary, providing the first direct evidence of planets outside our solar system, and challenging our understanding of planetary formation and the potential for life in other star systems. Following this, the methods for discovering exoplanets expanded significantly, with techniques such as the transit method and the radial velocity method becoming popular, enabling astronomers to identify thousands of exoplanets in the years since. The discovery of these exoplanets has raised intriguing questions about their characteristics, compositions, and the possibility of finding life beyond Earth, leading to a new era of exploration and research in the field of astronomy. The radial velocity method, also known as the Doppler method, is a fascinating technique used by astronomers to detect exoplanets, which are planets located outside our solar system. This method relies on observing tiny movements of a star caused by the gravitational pull of an orbiting planet. When a planet orbits a star, it doesn't just pull the star directly toward it. Instead, both the star and the planet orbit around a common center of mass, which is usually located just outside the surface of the star due to the star's much larger mass. As a result of this motion, the star experiences a slight wobble, which can be detected using precise measurements of its light. As the star moves toward us, the light it emits is compressed, leading to a shift towards the blue end of the spectrum, and when it moves away, the light is stretched, resulting in a shift towards the red end of the spectrum. This phenomenon, known as the Doppler effect, is crucial for the radial velocity method. By measuring these shifts in the star's spectrum, astronomers can determine the presence of a planet as well as estimate its mass and orbital distance. The magnitude of the radial velocity shift, often measured in meters per second, can indicate how massive the planet is and how close it is to the star. For instance, a larger planet will exert a stronger gravitational tug on the star, resulting in a more significant shift in the star's light spectrum. Conversely, a smaller planet might produce a much smaller shift, making it more challenging to detect. The method is most effective for detecting large planets that are close to their stars, often referred to as hot Jupiters. But it can also identify smaller Earth-like planets if the observational techniques are sufficiently advanced. One of the most exciting aspects of the radial velocity method is its ability to provide information about the planetary system as a whole, including the potential for multiple planets orbiting the same star. When multiple planets are present, they can interact with each other gravitationally, which can lead to complex patterns in the star's radial velocity shifts, allowing astronomers to infer the number of planets and their respective masses. Over the years, this method has led to the discovery of thousands of exoplanets, significantly expanding our understanding of the diversity of planetary systems in our galaxy. Notable missions, such as the Kepler Space Telescope, have utilized the radial velocity method to complement its primary transit observation technique. The transit method and the radial velocity method are two prominent techniques used in the search for exoplanets, each with its own unique approach and advantages. The transit method primarily relies on observing the slight dimming of a star's light, which occurs when a planet passes in front of it, blocking a small portion of the light. This dimming is usually measured by space telescopes like the Kepler Space Telescope or the Transiting Exoplanet Survey Satellite, commonly known as TESS. When a planet transits, it creates a characteristic light curve, a graph that shows the brightness of the star over time. By analyzing this light curve, astronomers can determine important details about the planet, such as its size, orbital period, and distance from the star, as well as inferring the planet's atmospheric composition if conditions allow. The transit method is particularly effective for detecting planets that orbit close to their stars, as these transits occur more frequently, allowing for a greater chance of detection. On the other hand, the radial velocity method, often referred to as the Doppler method, detects exoplanets by observing the gravitational influence they exert on their host stars. As a planet orbits a star, it causes the star to wobble slightly, moving towards and away from the observer. This movement alters the star's light spectrum due to the Doppler effect, which shifts the wavelengths of light. When the star moves towards us, its light appears blue-shifted, while when it moves away, it appears red-shifted. By measuring these shifts in the star's spectrum, astronomers can determine the presence of an orbiting planet and its mass and distance. The radial velocity method is particularly useful for detecting more massive planets, such as gas giants, that exert a stronger gravitational pull on their stars, leading to more noticeable shifts in the star's spectrum. In summary, while both methods aim to uncover the mysterious worlds beyond our solar system, they do so in fundamentally different ways, with the transit method focusing on the light changes from a star when a planet passes in front of it, and the radial velocity method concentrating on the subtle movements of a star caused by the gravitational tug of an orbiting planet. Each method complements the other, providing a more comprehensive understanding of the exoplanet population and their characteristics within our galaxy. Space telescopes play a crucial role in the detection of exoplanets, which are planets located outside our solar system orbiting other stars. Unlike ground-based telescopes, which are limited by the Earth's atmosphere, space telescopes can observe the universe in a clearer, more detailed manner, free from atmospheric distortion and light pollution. One of the primary methods used by space telescopes to detect exoplanets is the transit method, which involves observing a star's brightness over time. When a planet passes in front of its host star, it causes a slight dip in the star's brightness, and this tiny change can be measured with incredible precision. The Kepler Space Telescope, launched in 2009, was specifically designed for this purpose, monitoring the brightness of over 150,000 stars simultaneously, and it discovered thousands of exoplanets during its mission. Moreover, space telescopes can also utilize the radial velocity method, which detects the gravitational pull that an orbiting planet exerts on its host star. As a planet orbits, it causes the star to wobble slightly, resulting in shifts in the star's spectrum detectable through precise measurements. Instruments aboard telescopes like the Hubble Space Telescope and the Transiting Exoplanet Survey Satellite have provided valuable data using this method, helping astronomers confirm the presence of exoplanets and learn more about their characteristics. Additionally, space telescopes are crucial for characterizing exoplanets, particularly in studying their atmospheres. When light from a star passes through the atmosphere of an exoplanet, it can leave unique signatures, allowing astronomers to identify the presence of various gases such as water vapor, carbon dioxide, and methane. The James Webb Space Telescope, which launched in December 2021, is set to enhance our understanding of exoplanet atmospheres, providing deeper insights into their composition and potential habitability, showcasing the immense potential for future discoveries. The ability to observe exoplanets in different wavelengths of light, including infrared, ultraviolet, and visible light, gives space telescopes a unique advantage. This multi-wavelength approach enables scientists to gather comprehensive data about these distant worlds, revealing their temperature, atmosphere, and even surface conditions. As technology advances, the role of space telescopes continues to expand, paving the way for more sensitive instruments that can detect smaller Earth-like exoplanets orbiting within the habitable zones of their stars. In summary, the invaluable contributions of space telescopes in the detection and characterization of exoplanets have revolutionized our understanding of the universe. The concept of the habitable zone, often referred to as the Goldilocks zone, is a fascinating aspect of exoplanet studies, and it plays a crucial role in our search for extraterrestrial life. This zone is defined as the region around a star where conditions may be just right for liquid water to exist on the surface of a planet, and as we know, water is essential for life as we understand it. The distance from a star, the star's brightness, and the planet's atmosphere all influence whether a planet falls within this habitable zone. For instance, if a planet is too close to its star, it may become too hot, causing any water to evaporate, while a planet that is too far away may be too cold, leading to ice-covered surfaces. The habitable zone is not a fixed area. It varies depending on the type and size of the star. For example, the habitable zone around a small cooler star like a red dwarf is much closer than that around a larger hotter star like our Sun. Understanding this zone is vital because when astronomers discover exoplanets, they want to know if these planets lie within their star's habitable zone, as this increases the chances that they could support life. Moreover, the importance of the habitable zone extends beyond just the presence of water. It also involves other factors such as the planet's atmosphere, which can protect life from harmful radiation and help maintain a stable climate. For example, Venus is situated within our Sun's habitable zone, yet its thick atmosphere creates a runaway greenhouse effect, making it too hot for life as we know it. Conversely, Mars, which is on the outer edge of the habitable zone, has conditions that are harsh, but it still presents some intriguing possibilities for past or present microbial life. The study of these zones therefore helps scientists understand not only where to look for potentially habitable worlds, but also what conditions might allow for life to thrive, or conversely to be impossible. In the realm of exoplanet research, scientists use various methods to identify and analyze exoplanets within habitable zones. One common technique is the transit method, where astronomers observe a slight dimming of a star's light as a planet passes in front of it, allowing them to determine the planet's size and orbit. By knowing the planet's distance from its star, researchers can then assess whether it falls within the habitable zone. Recent advancements in technology have significantly improved transit methods, particularly within the realms of space exploration and transportation. One of the most notable developments has been in propulsion systems, where innovations such as ion thrusters and plasma propulsion are being implemented. These advanced systems allow spacecraft to travel faster and more efficiently, utilizing less fuel compared to traditional chemical rockets. For instance, NASA's Dawn spacecraft, which utilized ion propulsion, was able to orbit two distant celestial bodies, Vesta and Ceres, showcasing how these technologies can open up new avenues for exploration. Moreover, the integration of artificial intelligence and machine learning has revolutionized navigation and control systems in spacecraft. These intelligent systems can analyze vast amounts of data in real time, adjusting flight paths and making decisions that enhance mission safety and efficiency. This is particularly important for missions to distant planets where human intervention may not be immediately possible. The autonomous capabilities developed through these technologies enable spacecraft to perform complex maneuvers, such as landing on other planets or moons, with a high degree of precision. Additionally, advancements in material science have led to the creation of lighter, stronger materials, which are crucial for building spacecraft that can withstand the harsh environments of space. For example, carbon composites and advanced alloys are now commonly used, reducing the overall weight of the spacecraft while still providing the needed structural integrity. This reduction in weight allows for more payload capacity, enabling missions to carry more scientific instruments or supplies. The development of reusable rocket technology, pioneered by companies like SpaceX with their Falcon 9 rocket, has also transformed the economics of space travel. By landing and reusing rockets, the cost of launching payloads into space has decreased dramatically. This has opened up new opportunities for both governmental and commercial space endeavors, making it more feasible to conduct a variety of missions from satellite deployment to crewed space flights. Furthermore, the advent of advanced communication technologies, such as laser communication, is enhancing data transmission between spacecraft and Earth. These systems can send information at much higher rates than traditional radio frequency systems, allowing for quicker transmission of scientific data and enhancing real-time communication during missions. In terms of ground support, improvements in simulation technologies and virtual reality are providing astronauts and mission planners with better training and preparation tools. Advanced simulations can recreate the conditions of space, enabling crew members to practice emergency procedures and mission protocols in a safe environment, helping to ensure success when they are actually in space. Finally, the growing collaboration between private and public sectors is fostering rapid technological advancements in transit methods initiatives. The Kepler Space Telescope, launched by NASA in 2009, has dramatically changed our understanding of exoplanets, which are planets outside our solar system. By employing a technique known as the transit method, which involves observing the slight dimming of a star when a planet passes in front of it, Kepler monitored over 150,000 stars in the Milky Way. It detected thousands of these transits, leading to the discovery of more than 2,600 confirmed exoplanets. This was a monumental leap from just a handful of known exoplanets before its mission began. One of the telescope's major contributions is its ability to identify many Earth-sized and potentially habitable planets. In fact, Kepler has found hundreds of planets in the so-called Goldilocks zone, the region around a star where conditions might be just right for liquid water to exist. Moreover, Kepler's data has allowed scientists to study the diversity of planetary systems, revealing that many stars host multiple planets, and some systems have planets that are very different from those in our solar system. With discoveries of hot Jupiters, which are gas giants that orbit very close to their stars, and super-Earths, which are rocky planets larger than Earth but smaller than Neptune, these findings suggest that planetary formation and migration can occur in ways that we had not previously understood. The telescope has also contributed to the understanding of the frequency of exoplanets. Studies based on Kepler's findings suggest that there could be more planets than stars in our galaxy, a staggering idea that expands the possibilities for finding life elsewhere in the universe. Kepler's mission did not just stop at finding new worlds. It also provided valuable insights into the atmospheres of some exoplanets. By analyzing the light that filters through a planet's atmosphere during a transit, scientists can gather clues about the planet's composition, weather patterns, and potential for hosting life. This kind of analysis has helped to identify the presence of molecules like water vapor, carbon dioxide, and methane in exoplanetary atmospheres. As a result of these discoveries, Kepler has sparked a new field of research focused on characterizing exoplanets and understanding their potential habitability. Additionally, the telescope's extensive data set has enabled researchers to refine their models of planetary formation and evolution by comparing the sizes and orbits of exoplanets with those of the planets in our own solar system. The radial velocity method, often referred to as the Doppler method, is a widely recognized technique used to detect exoplanets, which are planets outside our solar system. This method primarily relies on observing the tiny wobbles in a star's position caused by the gravitational pull of an orbiting planet. When a planet orbits a star, it creates a slight tug, causing the star to move in a small circle or ellipse, which in turn affects the star's light spectrum due to the Doppler effect, where the wavelengths of light shift depending on the star's motion relative to Earth. However, despite its success in identifying many exoplanets, especially larger ones, the radial velocity method has several limitations, particularly when it comes to detecting smaller exoplanets. One significant limitation is the sensitivity of the method. The radial velocity technique is most effective for detecting large planets like Jupiter, which exert a stronger gravitational pull on their host stars. Smaller planets such as Earth-sized or even super-Earths produce much weaker signals, making them harder to detect against the noise of the star's own movement and other astrophysical phenomena. This means that to identify smaller exoplanets, astronomers require extremely precise measurements of a star's velocity, often needing to detect changes on the order of meters per second, which can be quite challenging, especially for stars that are less massive or exhibit their own motion. Another limitation arises from the fact that the radial velocity method is biased toward finding planets that are close to their stars. This is because a planet's gravitational influence diminishes with distance, making it less likely to cause noticeable shifts in the star's spectrum if it is orbiting far away. Most of the exoplanets discovered through this method are located in short-period orbits, often within a few days, which may not provide a complete picture of the diversity of planetary systems, especially those that resemble our own, with Earth-like planets in habitable zones. Additionally, the radial velocity method struggles with multiple planet systems. In cases where multiple planets orbit the same star, their gravitational interactions can complicate the analysis, and the signals from different planets can overlap, leading to challenges in accurately determining the mass and orbit of each individual planet. This complexity can result in false positives, where the detected signal might be misattributed to a single planet rather than being the result of multiple planets influencing the star's motion. Another factor to consider is the influence of stellar activity. Direct imaging is a fascinating method for detecting exoplanets, which are planets outside our solar system, and it involves capturing actual pictures of these distant worlds rather than inferring their existence through indirect methods. This technique relies on advanced telescopes and sophisticated imaging technology to distinguish the faint light of exoplanets from the overwhelming brightness of their parent stars. When we look at a star, it often shines so brightly that it can completely overshadow the light reflected or emitted by an orbiting planet, making it extremely difficult to spot. To overcome this challenge, astronomers use several strategies, one of which involves the use of special instruments called coronagraphs, which can block out the starlight while allowing the dimmer light from the planet to pass through, creating a clearer image of the exoplanet. Another important tool in the direct imaging toolbox is adaptive optics, which helps to correct for distortions caused by Earth's atmosphere. Earth's atmosphere can bend and blur the light coming from space, so adaptive optic systems make real-time adjustments to the telescope's mirror to counteract these effects, resulting in sharper images. This technology is particularly useful when observing distant stars, as it enables astronomers to resolve smaller features and better distinguish between the star and its surrounding planets. Additionally, astronomers often target young stars, which are surrounded by protoplanetary disks of gas and dust, as these environments are more likely to host detectable exoplanets. The light emitted by these young planets is more pronounced, making it easier to capture in images. The process of direct imaging not only allows scientists to find exoplanets, but it can also provide valuable information about their atmospheres and compositions, as the light from the planet can be analyzed to determine the presence of certain molecules like water vapor, methane, or carbon dioxide. Direct imaging has led to some remarkable discoveries. For example, the very first direct images of exoplanets were captured in 2004 when astronomers took pictures of a planet called HR 8799b, which orbits a star about 129 light-years away from Earth. This was a groundbreaking achievement as it showcased the potential of direct imaging as a viable method for observing exoplanets. And since then, numerous other planets have been captured in images using this technique, deepening our understanding of the diversity of planetary systems beyond our own, and bringing us closer to answering fundamental questions about the existence of life elsewhere in the universe. While direct imaging has its limitations, its potential for future discoveries remains vast. Direct imaging of exoplanets presents several significant challenges, primarily due to the vast distances involved, the brightness of their host stars, and the need for advanced technology to capture such faint signals. One of the foremost difficulties is the overwhelming glare from the stars themselves, which can overshadow the light reflected or emitted by planets orbiting around them. For instance, when we look at a star, the light is so intense that it creates a sort of light pollution, making it nearly impossible to see the much dimmer exoplanets nearby. This is why astronomers often employ techniques like coronagraphy, which allows them to block out the star's light, creating a sort of shadow where they can look for planets. But even this method has its limitations, as it can be challenging to completely eliminate the star's light without affecting the light of the exoplanet. Additionally, the distances to exoplanets are astounding, often measured in light years, meaning that the light we receive from these planets is incredibly faint, requiring highly sensitive instruments to detect. The instruments must not only be sensitive, but also capable of distinguishing between the light from the planet and that from the star, which is no small feat. The technology used for direct imaging, such as adaptive optics, aims to correct for the distortion caused by Earth's atmosphere, which can blur the images captured by telescopes, thus complicating the imaging process even further. Another significant challenge is the relative youth of many exoplanets. Young planets can be bright, but they may also be surrounded by dust and gas, which can obscure the view, while older planets may cool down and become less visible over time. This variability means that astronomers need to time their observations carefully to catch planets when they are most observable. Moreover, the orientation of the planetary system plays a crucial role. Planets need to be positioned at a favorable angle relative to Earth for us to see them clearly, which is often a rare alignment. The analysis of the data collected is also complex. Once the images are captured, astronomers must sift through a significant amount of information to confirm that what they see is indeed an exoplanet, and not just noise or artifacts created by the instruments or the atmosphere. This requires sophisticated algorithms and often a considerable amount of time to verify their findings against existing databases of known stars and celestial phenomena. All these challenges highlight the intricate nature of direct imaging of exoplanets, requiring a blend of advanced technology, precise timing, and careful analysis to overcome. Gravitational microlensing is a fascinating phenomenon that occurs when a massive object such as a star passes in front of a more distant light source like another star or galaxy, causing the light from that faraway object to bend around the massive object due to the effects of gravity. This bending of light can create a temporary magnification of the distant object, making it appear brighter than usual. This effect, predicted by Einstein's theory of general relativity, provides astronomers with a unique tool to detect distant exoplanets, which are planets located outside our solar system. When astronomers observe a microlensing event, they look for changes in brightness in the light of the background star. If there's a planet orbiting the foreground star, it can also cause additional magnification, leading to a characteristic signature in the light curve, which is the graph of brightness over time. These signatures can indicate the presence of a planet, its size, and its distance from the star. The process works because the gravitational field of the foreground star acts like a lens focusing the light from the background star. If there is a planet in orbit around the foreground star, the planet's gravity can further affect the light path, creating a second peak in the light curve, which is distinct from the peak caused by the star alone. This additional peak can reveal the planet's mass and its distance from the star, allowing astronomers to infer its characteristics. Gravitational microlensing is particularly useful for detecting exoplanets that are far away and those that may not emit light themselves, as it relies on the gravitational effects rather than direct observation. One of the most exciting aspects of gravitational microlensing is its ability to uncover planets that are not easy to spot with traditional methods like the transit method, which relies on detecting the small dip in light when a planet passes in front of its star. Microlensing can detect planets at various distances from their stars, including those in the so-called habitable zone where conditions might be right for life. This opens up new possibilities for understanding the distribution and variety of planetary systems throughout the universe. In recent years, several projects including the Kepler mission and the microlensing observations in astrophysics, or MOA, have successfully used this technique to identify numerous exoplanets, expanding our knowledge of the cosmos and the diversity of worlds that exist beyond our own. As technology continues to advance, we can expect even more discoveries through this remarkable method. Astrometry, a technique that involves measuring the precise positions and movements of stars in the sky, offers several significant advantages for detecting exoplanets. One of the most notable benefits is its ability to detect planets that are relatively far from their host stars, which can be challenging for other methods, such as the transit method, that mainly focus on planets that pass in front of their stars from our viewpoint. This means that astrometry can reveal the presence of larger planets that might not cause noticeable dimming of their star, allowing astronomers to discover a wider range of planetary systems, including those with gas giants, which could be located in the outer regions of their star systems. Another advantage of astrometry is its effectiveness at identifying multiple planet systems. When a star has more than one planet, the gravitational interactions between these planets can cause the star to wobble slightly, and astrometry can measure this tiny movement very precisely. This capability allows scientists to estimate the masses and orbits of these planets, providing valuable insights into the dynamics of the system as a whole. Moreover, astrometry can also help in confirming the existence of exoplanets that have been detected through other methods, as it provides an independent way to verify their presence. Astrometry is particularly useful for detecting exoplanets around nearby stars, which is a crucial factor for follow-up studies such as characterizing the atmospheres of these planets or searching for signs of habitability. Since the closest stars are often the best targets for detailed study, the ability of astrometry to detect planets orbiting these stars makes it a critical tool in the ongoing search for potentially habitable worlds. Additionally, astrometry can provide information about the inclination of a planet's orbit, which helps scientists understand its potential climate and atmospheric conditions, as the tilt of a planet can influence its temperature and weather patterns. Furthermore, with advancements in technology, especially with space-based observatories, astrometry has become even more precise. Instruments like the European Space Agency's Gaia mission are set to revolutionize the field by providing high-precision measurements of stellar positions. These observations can help detect even smaller planets that exert a weaker gravitational pull on their stars, expanding our knowledge of exoplanet diversity. This precision could lead to the discovery of Earth-like planets in the habitable zones of their stars, which is a primary goal of modern astronomy. Astrometry also minimizes the biases inherent in other detection methods, as it does not rely on the brightness of stars or the alignment of planets. Ground-based observatories have significantly enhanced the search for exoplanets thanks to their advanced technologies, strategic locations, and collaborative efforts among scientists around the world. One of the most notable advancements is the implementation of high-precision radial velocity measurements, which allows astronomers to detect the slight wobble of stars caused by the gravitational pull of orbiting planets. These ground-based telescopes equipped with sophisticated spectrographs can measure tiny shifts in the star's light spectrum, indicating the presence of an exoplanet, often even when it is too faint to be seen directly. In addition, ground-based observatories benefit from their ability to observe a wide range of wavelengths, including infrared and optical light, which can provide crucial information about the atmospheres of exoplanets. Instruments like the Keck Observatory in Hawaii, with its adaptive optic systems, can correct for the blurring effects of Earth's atmosphere, enabling sharper images and more accurate measurements. This technology has allowed astronomers to study the light from distant stars and their planets in unprecedented detail, revealing atmospheric compositions, temperatures, and even weather patterns on these distant worlds. Furthermore, the collaborative nature of ground-based observatories has fostered a global effort in the hunt for exoplanets. Observatories like the European Southern Observatory in Chile and the Las Campanas Observatory work together, sharing data techniques and findings, which accelerates our understanding of planetary systems beyond our own. The TESS mission, although space-based, also coordinates with ground-based telescopes to follow up on its discoveries, allowing astronomers to confirm the existence of newly detected planets and gather more information about them. Additionally, citizen science has played a role in enhancing these efforts, where amateur astronomers using backyard telescopes and online platforms contribute to the discovery of exoplanets by analyzing data and identifying potential candidates. This democratic approach to science not only increases the number of observations, but also engages a passionate community of individuals who are excited about the prospect of finding other worlds. Moreover, the increasing capabilities of ground-based observatories have led to the discovery of many Earth-sized planets in the habitable zones of their stars, which are particularly exciting because they may have conditions suitable for life. Instruments like the HARPS spectrograph have discovered thousands of exoplanets, including those that could be rocky and potentially capable of supporting life. The combination of advanced technology, collaborative efforts, and citizen involvement has transformed ground-based observatories into powerful tools in the ongoing quest to find and study exoplanets. The Transiting Exoplanet Survey Satellite, known as TESS, plays a pivotal role in our quest to discover and study exoplanets, those intriguing worlds that orbit stars outside our solar system. Launched by NASA in April 2018, TESS is designed to build upon the legacy of the Kepler mission, which was groundbreaking in identifying thousands of exoplanets. But it takes a different approach, focusing primarily on the closest and brightest stars in our neighborhood. This focus is significant as it allows for a more detailed examination of these planets, giving astronomers the chance to learn about their atmospheres, compositions, and potential habitability, which is crucial in understanding the diversity of planetary systems, including our own. The TESS mission employs a technique called the transit method, which detects exoplanets by observing the slight dimming of a star's light as a planet passes in front of it. This method is remarkably effective, especially with TESS's advanced capabilities, as it can monitor large sections of the sky for extended periods, capturing more transits and thus identifying more planets than previous missions. Additionally, TESS has the advantage of surveying a wide range of star types, which is essential for classifying exoplanets into different categories based on their characteristics. This diversity enables scientists to explore a variety of planetary environments, from gas giants to potentially rocky Earth-sized planets located in the habitable zone of their stars, where conditions might be just right for liquid water to exist. The mission's goal is to catalog thousands of new exoplanets, and so far it has already discovered thousands of candidates, providing a wealth of data that researchers can analyze. These findings are not only exciting in their own right, but also serve as a launching pad for future observations with powerful telescopes like the James Webb Space Telescope, which can study the atmospheres of these newly discovered planets in detail. Moreover, TESS is significant because it fosters collaboration among scientists around the world, as the data it collects is made available to the public, allowing both professional and amateur astronomers to participate in the search for exoplanets. This open-access approach encourages a global effort in exoplanet research, leading to greater discoveries. The mission also emphasizes the importance of finding planets that are not only near to us, but also similar to Earth, as understanding how common Earth-like planets are in the universe could provide insight into the possibilities of life beyond our planet. Overall, TESS represents a crucial step forward in our exploration of the cosmos. Transit timing variations, often abbreviated as TTVs, play a crucial role in the discovery of exoplanets, particularly in systems with multiple planets. When we talk about transits, we refer to the event when a planet passes in front of its host star from our point of view, causing a temporary dimming of the star's light. Astronomers using telescopes can detect these small changes in brightness, and by carefully monitoring the timing of these transits, they can gather important information about the planets in a given system. Now the interesting part comes into play when multiple planets orbit a star. These planets exert gravitational forces on each other, which can lead to variations in their orbits. As a result, the timing of their transits can shift slightly, either getting earlier or later than expected. This phenomenon is what we call transit timing variations. By observing these variations, scientists can infer the presence of additional planets that have not yet been directly observed. For example, if a known exoplanet is seen to transit its star earlier than predicted, this could suggest that another more massive planet is tugging on it gravitationally, altering its orbit. In this case, the TTVs provide indirect evidence of the additional planet's existence, allowing researchers to calculate its mass and orbit, even if the planet itself is too faint to be seen directly. This method is particularly effective in systems with multiple planets, where the interactions between them can create complex patterns of timing variations. Astronomers have successfully used TTVs in many cases, including with the Kepler space mission, which discovered thousands of exoplanets using the transit method. By analyzing the transit timing variations of these planets, scientists have identified additional bodies in various systems, expanding our understanding of how planets form and interact. The TTV technique highlights the intricate dance of celestial bodies, as well as the gravitational relationships that govern them, which can lead to the discovery of new worlds beyond our own solar system. In essence, transit timing variations serve as a powerful tool in the exoplanet discovery toolkit, providing insights into the dynamic nature of planetary systems. And as telescopes become more advanced, and as our ability to measure these tiny variations improves, we can expect to uncover even more hidden worlds, revealing the rich complexity of the universe and our place within it. Hot Jupiters, which are a type of exoplanet, are gas giants that orbit very close to their stars, often completing a full orbit in just a few days. Unlike the gas giants in our solar system, which are much farther from the Sun, these planets are characterized by their high temperatures due to the intense radiation they receive from their host stars, creating atmospheric conditions that can be quite extreme. The discovery of hot Jupiters was surprising to astronomers, as their existence challenges traditional theories of planet formation, which suggested that gas giants should form far from their stars, where it is cooler, allowing them to gather the necessary materials for their formation without being subjected to excessive heat. Detecting hot Jupiters poses unique challenges for astronomers, primarily because of their proximity to their stars, which can make it difficult to distinguish the light of the planet from the light of the star itself. The common methods used for exoplanet detection, such as the transit method and the radial velocity technique, can be less effective with hot Jupiters. In the transit method, a planet passes in front of its star, causing a slight dimming in the star's light. But because hot Jupiters are so close to their stars, the transit can be very brief, sometimes just a few hours, and can easily be overlooked if the observation isn't timed perfectly. Furthermore, because hot Jupiters often have high temperatures, their atmospheres can be quite dynamic, leading to rapid changes that can affect the observed light during transits. In addition to the transit method difficulties, the radial velocity method, which measures the star's wobble caused by the gravitational pull of the orbiting planet, can also be challenging with hot Jupiters. The strong gravitational interactions between the planet and its star can lead to complex motion, making it tricky to accurately determine the planet's mass and orbital characteristics. Moreover, hot Jupiters can have very eccentric orbits, adding another layer of complexity to their detection. Another challenge arises when considering the atmospheric composition of hot Jupiters. Their proximity to their stars means that they can be subject to extreme weather patterns, and the intense heat can lead to atmospheric phenomena that are unlike what we observe on cooler planets. This can make it difficult to interpret data collected from these planets, as atmospheric models must account for the unique conditions present on hot Jupiters. The presence of cloud storms and high-speed winds can all affect how light passes through the atmosphere. Machine learning has revolutionized the way scientists detect and analyze exoplanets, those intriguing worlds beyond our solar system, which have captivated the imagination of both scientists and the general public alike. Traditionally, exoplanet detection relied heavily on methods such as the transit method, where astronomers would monitor the brightness of stars looking for periodic dips that signal a planet passing in front of them, or the radial velocity method, which measures the wobble of a star caused by the gravitational pull of an orbiting planet. However, these methods can be time-consuming, labor-intensive, and often require human intuition and experience to sift through vast amounts of data, leading to the possibility of missed discoveries. This is where machine learning steps in, offering powerful tools to analyze complex datasets quickly and efficiently, which is particularly advantageous in the era of big data. For instance, machine learning algorithms can process data from space telescopes like Kepler and TESS, the Transiting Exoplanet Survey. Satellite, examining thousands of stars simultaneously, identifying patterns and making predictions about potential exoplanets with a speed and accuracy that surpasses human capabilities. Researchers have trained algorithms using known exoplanet data, teaching them to recognize the subtle signals that indicate a planet's presence even in the midst of noise from other celestial phenomena. This approach has led to the discovery of new exoplanets that might have gone unnoticed, as machine learning can flag candidates that are worth further study, streamlining the discovery process. Moreover, machine learning is not just limited to detection. It also plays a crucial role in the analysis of the characteristics of these exoplanets. Once a potential exoplanet is detected, machine learning can help determine its size, composition, and even its atmosphere by analyzing the light spectra that are emitted or absorbed by the planet. This analysis can reveal vital information about the planet's temperature, atmospheric pressure, and potential habitability, which are critical factors in understanding whether these distant worlds could support life. By training models on existing data from known exoplanets, researchers can create predictive models that help assess the likelihood of similar planets having comparable conditions. In addition to this, machine learning techniques can also assist in classifying exoplanets into different categories based on their features, such as gas giants, rocky planets, or potentially habitable worlds. This classification helps scientists understand the diversity of planetary systems and the processes that lead to the formation of different types of planets. Furthermore, advancements in deep learning algorithms have improved the accuracy of these classifications even more. Characterizing exoplanet atmospheres plays a crucial role in the search for life beyond our solar system, as it allows scientists to gather vital information about the conditions on these distant worlds. When astronomers discover an exoplanet, particularly one located in the habitable zone of its star, the next logical step is to analyze its atmosphere, since the atmosphere can reveal essential clues about the planet's potential to support life. By studying the composition of an exoplanet's atmosphere, researchers can identify the presence of key molecules such as carbon dioxide, methane, and water vapor, which are often associated with biological processes on Earth. For instance, the detection of oxygen or ozone, which are produced by living organisms, could indicate that a planet has life forms similar to those on our planet. Furthermore, the presence of certain gases in specific ratios can serve as biosignatures, which are indicators that point to biological activity. Moreover, the methods used to characterize exoplanet atmospheres, such as transmission spectroscopy, allow scientists to observe how starlight filters through an exoplanet's atmosphere during a transit. This technique provides a spectrum of the light, revealing the chemical fingerprints of various gases present. Each gas absorbs light at specific wavelengths, so by examining these absorption features, astronomers can deduce the composition and even the temperature and pressure of the atmosphere. This not only helps in determining whether the atmosphere is thick enough to retain heat and sustain liquid water, but it also gives insights into the planet's climate and weather patterns, which are essential for understanding its habitability. Additionally, characterizing atmospheres can help identify planets that may have conditions similar to Earth, allowing scientists to narrow down their search for potentially habitable environments. For example, exoplanets that exhibit a greenhouse effect, which could keep temperatures suitable for liquid water, are particularly interesting. This understanding of atmospheric dynamics can also reveal how different types of planets evolve and how their atmospheres may change over time, indicating the presence or absence of life. Importantly, the study of exoplanet atmospheres is not just about finding life, but also about understanding the different ways in which life could exist. Some exoplanets might have extremely different atmospheres compared to Earth, yet still support life forms adapted to those conditions. By expanding our knowledge of atmospheric compositions, we can begin to consider the diverse possibilities of life beyond our own experience. As technology advances, the tools for characterizing these atmospheres continue to improve. Once scientists detect an exoplanet, which is a planet outside our solar system, they employ several techniques to determine its size and mass, both of which provide vital information about the exoplanet's characteristics and potential habitability. One of the primary methods used to ascertain the size of an exoplanet is the transit method. This technique involves observing a star and looking for periodic dimming, which occurs when an exoplanet passes in front of it, blocking a portion of the star's light. By measuring the amount of light that is blocked and how long the transit lasts, scientists can infer the size of the exoplanet in relation to its host star. For instance, if the dip in brightness is significant, it indicates a larger planet, whereas a smaller dip suggests a smaller planet. Additionally, using the transit method, scientists can determine the radius of an exoplanet by comparing it to the size of the star, which is usually known from other observations. This allows researchers to calculate the planet's size in terms of Earth radii. To measure the mass of the exoplanet, scientists often use the radial velocity method, also known as the Doppler method. This technique measures the wobble of a star caused by the gravitational pull of an orbiting planet. When a planet orbits a star, it exerts a gravitational force causing the star to move slightly in response. This movement affects the light spectrum of the star, shifting it toward the red end when the star moves away and toward the blue end when it moves closer. By measuring these shifts, scientists can determine the star's velocity changes, and using Newton's laws of motion and gravitation, estimate the mass of the planet. Sometimes these two methods are used together, allowing for a more accurate determination of both size and mass. Furthermore, the observations can be supplemented by data from space telescopes like the Kepler Space Telescope or the Transiting Exoplanet Survey Satellite, which have refined our ability to detect exoplanets and gather precise measurements. Another technique that has gained traction is direct imaging, where astronomers try to capture images of exoplanets by blocking out the star's light. Though this method is challenging, it can provide information about an exoplanet's size as well as its atmosphere if present. Moreover, scientists can also use gravitational microlensing, which occurs when a massive object passes in front of a distant star and magnifies its light. This technique can also provide clues about an exoplanet's mass and size. Spectroscopy plays a crucial role in the study of exoplanet atmospheres, offering scientists a powerful tool to analyze the light emitted, absorbed, or scattered by these distant worlds. When a planet passes in front of its host star, a phenomenon known as a transit, some of the starlight filters through the planet's atmosphere. This light interacts with the molecules present in the atmosphere, and this interaction causes specific wavelengths of light to be absorbed, which can be detected and measured. By using spectroscopy, researchers can identify these absorption lines, which correspond to different elements and compounds, allowing them to determine the composition of the atmosphere. The technique involves separating light into its component colors, much like a prism does. When the light from the star passes through the exoplanet's atmosphere, the spectrum shows dark lines at specific wavelengths representing the gases that are present. For example, if water vapor, carbon dioxide, or methane exists in the atmosphere, they will absorb light at particular wavelengths, creating distinctive signatures that scientists can recognize. This process is essential for understanding not only what gases are present, but also their abundances, which can give clues about the planet's potential habitability. Moreover, spectroscopy can also be used to study the temperature and pressure of an exoplanet's atmosphere, as different gases behave differently under varying conditions. By analyzing the spectrum, scientists can infer the thermal structure of the atmosphere, which helps in understanding the planet's climate and weather patterns. This information is vital, especially when comparing exoplanets to Earth, as it can reveal whether they have conditions that might support life. In addition, spectroscopy is not limited to just the visible light spectrum. It can also be applied across other wavelengths, such as infrared and ultraviolet. Infrared spectroscopy, for example, is particularly useful for detecting molecules that might be present in colder environments, as many gases exhibit strong absorption features in the infrared range. This capability allows scientists to study a broader range of exoplanets, including those that are too cool or distant to observe in visible light. Furthermore, recent advancements in technology have improved our ability to conduct spectroscopy on exoplanets. Space telescopes like the Hubble Space Telescope and the upcoming James Webb Space Telescope are equipped with advanced spectrographs that can collect high-resolution spectra from distant worlds. These instruments allow astronomers to analyze multiple exoplanets, simultaneously expanding our understanding of the diversity of planetary atmospheres in our galaxy as researchers continue to refine their spectroscopic techniques. Advancements in infrared technology have significantly transformed the field of exoplanet detection, allowing astronomers to observe celestial objects that were previously hidden from view. By utilizing infrared wavelengths, which are longer than visible light, scientists can detect the heat emitted by planets, even those that are in the habitable zone of their stars. These advancements have made it possible to identify planets that may be similar to Earth, thus expanding our understanding of potential habitats beyond our own solar system. One of the key breakthroughs in this area has been the development of space-based telescopes, such as the James Webb Space Telescope, which is specifically designed to operate in the infrared spectrum, allowing it to peer through the dust and gas that often obscures our view of distant stars. This telescope can detect the heat signatures of exoplanets, and it can also analyze their atmospheres by studying the light that filters through them when the planets pass in front of their host stars. This process, known as transit photometry, has become a powerful method for characterizing the chemical composition of an exoplanet's atmosphere, identifying molecules like water vapor, carbon dioxide, and even oxygen, which are crucial for understanding the potential for life. Furthermore, advancements in infrared technology have improved our ability to differentiate between stars and their closely orbiting planets, as many exoplanets are found in close proximity to their stars, which can make detection challenging. New instruments and techniques, such as adaptive optics and coronagraphy, allow astronomers to block out the light from a star, making it easier to spot the faint glow of an orbiting planet. Infrared observations are particularly valuable because planets emit more radiation at these longer wavelengths, especially if they are warm enough to support liquid water. This means that even small rocky planets can be detected if they are in the right conditions. In addition to this, infrared technology helps scientists to study the formation and evolution of planetary systems. By observing protoplanetary disks, the swirling clouds of gas and dust surrounding young stars, researchers can gain insights into how planets form and orbit. This understanding is crucial for piecing together the history of our own solar system, as well as the diversity of systems that exist throughout the universe. Moreover, ongoing developments in infrared detectors and imaging techniques continue to push the boundaries of what can be achieved in exoplanet research. Improved sensitivity and resolution allow astronomers to detect even fainter and more distant planets. The James Webb Space Telescope, often referred to as JWST, is a groundbreaking instrument that plays a crucial role in the field of exoplanet research, which is the study of planets beyond our solar system. Its primary purpose in this area is to observe the atmospheres and compositions of these distant worlds, providing valuable insights into their potential habitability, which is a key factor in the search for life beyond Earth. One of the unique features of JWST is its ability to capture infrared light, which allows it to peer through cosmic dust clouds and observe celestial objects that are often obscured from view by other telescopes, like the Hubble Space Telescope, which primarily focuses on visible light. When an exoplanet transits or passes in front of its host star, JWST can analyze the starlight that filters through the planet's atmosphere, enabling scientists to determine its chemical composition. This process, known as transmission spectroscopy, is instrumental in identifying the presence of molecules such as water vapor, carbon dioxide, and methane, which can indicate the potential for life. Moreover, JWST is equipped with advanced instruments such as the near-infrared spectrograph and the mid-infrared instrument, which enhance its ability to perform detailed studies of exoplanet atmospheres, allowing researchers to detect faint signals that other telescopes might miss. Another exciting aspect of JWST's mission is its capacity to observe exoplanets directly, a challenging endeavor due to the overwhelming brightness of their stars. By utilizing sophisticated techniques such as coronagraphy, JWST can block out starlight, enabling it to capture images of the planets themselves, which opens up new avenues for understanding their physical characteristics, climate, and potential for supporting life. This capability is particularly important for studying so-called super-Earths and mini-Neptunes, which are types of exoplanets that may have conditions suitable for life. Additionally, JWST aims to study the formation of planetary systems, shedding light on how different environments may influence the development of planets around various types of stars. By observing a wide range of star systems at different stages of formation, JWST can help scientists understand the common processes that lead to the creation of planets, including those that might host life. This contributes to a broader understanding of how our solar system fits into the larger tapestry of the universe and how unique or common Earth-like planets might be. The telescope's ability to peer deep into the universe also means it can study exoplanets in distant galaxies, offering a glimpse into planetary systems far beyond our own. Researchers harness data from exoplanet missions in various innovative ways with the goal of refining and enhancing detection algorithms which are crucial for identifying planets outside our solar system. By analyzing the vast amounts of data collected from missions like Kepler and TESS, scientists can develop more sophisticated models that help distinguish between actual exoplanets and false positives, such as stellar variability or noise in the data. One of the primary methods involves machine learning techniques where algorithms are trained on previously confirmed exoplanets using features such as light curves, which are graphs showing the brightness of a star over time. This training allows the algorithms to recognize patterns associated with the transit method where a planet passes in front of its star, causing a slight dimming of the star's light. Moreover, researchers utilize simulations and synthetic data, generating artificial light curves that replicate various scenarios of exoplanetary transits, including different planet sizes, orbital periods, and star types. This approach helps in testing the algorithms under controlled conditions, enabling scientists to identify weaknesses or blind spots in their detection strategies. Additionally, researchers often engage in cross-correlation techniques, comparing data from multiple observatories or missions, which not only strengthens the detection algorithms, but also provides a more comprehensive understanding of the planetary systems being studied. The ongoing collaboration among international teams, sharing findings and methodologies, also plays a pivotal role in improving these algorithms. By pooling data and insights, researchers can leverage a broader spectrum of information, allowing for the refinement of detection methods that account for a variety of stellar environments and planetary characteristics. Furthermore, the integration of different types of observational data, such as spectroscopy, allows scientists to analyze the atmospheres of exoplanets, providing another layer of information that can enhance detection algorithms, as atmospheric signatures can indicate the presence of certain types of planets. In essence, as researchers continue to gather more data from exoplanet missions, they are not only improving the algorithms used to detect new worlds, but also deepening our understanding of the diversity and complexity of planetary systems throughout the galaxy, paving the way for future discoveries and advancements in the field of astronomy. Super-Earths are a fascinating category of exoplanets defined as planets with a mass larger than Earth's, but significantly less than that of Uranus or Neptune, which are considered gas giants. These planets can range in size from about 1.25 to 2.5 times the Earth's radius, and they may have rocky surfaces and potentially even liquid water, making them intriguing candidates in the search for extraterrestrial life. Detecting super-Earths presents a unique challenge compared to gas giants, primarily because of their smaller size and varying atmospheres. One of the most common methods for discovering exoplanets, including super-Earths, is the transit method, which involves observing the slight dimming of a star's light as a planet passes in front of it. When a super-Earth transits its host star, the change in brightness is less pronounced than that caused by a gas giant due to the smaller size and mass of the super-Earth. This means that astronomers must have highly sensitive instruments capable of detecting even the tiniest changes in brightness to identify these smaller rocky worlds. Another technique used to detect super-Earths is the radial velocity method, which measures the movement of a star due to the gravitational pull of an orbiting planet. The presence of a super-Earth induces a smaller wobble in the star's motion than a gas giant would, which can make it more difficult to detect. Yet the technique has been successfully used to find numerous super-Earths. This method relies on precise measurements of spectral lines in starlight, which can shift due to the Doppler effect as the star moves toward and away from us. In addition to these methods, scientists also employ direct imaging, although this is more challenging for super-Earths than for gas giants, as the light from the star often overwhelms the faint light from the planet. However, with advancements in technology like coronagraphs and star shades, astronomers are beginning to successfully capture images of these distant worlds, providing further insight into their atmospheres and compositions. Furthermore, super-Earths may have a variety of atmospheric compositions, which can also be detected through spectroscopy. By analyzing the light that passes through a planet's atmosphere during a transit, scientists can infer the presence of various gases, helping to determine whether a super-Earth might be habitable. This process allows researchers to differentiate between the characteristics of super-Earths and gas giants, as gas giants typically have different atmospheric signatures. The study of exoplanets, which are planets located outside our solar system, has become a fascinating field, providing us with insights into planetary formation and evolution, and even the potential for life beyond Earth. By observing these distant worlds, scientists can gather crucial data about their composition, atmospheres, and orbits, which in turn reveals important clues about how they formed and how they compare to our own planetary system. For instance, when astronomers detect an exoplanet's size and mass, they can infer its density and composition, allowing them to categorize it as a gas giant, a rocky planet, or something in between. This classification helps researchers understand the conditions under which these planets formed, such as the distance from their host stars and the temperature of their environments, which are key factors in the development of different types of planets. Moreover, studying exoplanets can shed light on the processes of accretion and disk formation, which are fundamental to planetary formation. The presence of protoplanetary disks around young stars indicates that materials are clumping together, and understanding the dynamics of these disks, including the role of turbulence and magnetic fields, can help explain how solid bodies grow into larger planets. Additionally, by examining the diversity of exoplanetary systems, including those with unusual configurations, scientists can challenge and refine existing models of planetary formation, revealing that there is no one-size-fits-all approach to how planets develop. For example, the discovery of hot Jupiter's gas giants that orbit very close to their stars suggests that planets can migrate from their original formation zones, prompting further investigation into the forces that cause such dramatic shifts. Furthermore, the study of exoplanet atmospheres, particularly through techniques like transit spectroscopy, allows researchers to analyze the chemical compositions and weather patterns of these distant worlds. By comparing the atmospheres of exoplanets with different masses, temperatures, and distances from their stars, scientists can draw parallels to our own solar system, helping to refine theories about planetary atmospheres and their evolution over time. This knowledge not only enhances our understanding of how planets form, but also provides context for the habitability of planets, as certain atmospheric conditions may be more conducive to life than others. The exploration of exoplanets also sparks discussions about the role of stellar environments in shaping planetary systems. For example, the influence of stellar radiation and the presence of other celestial bodies can significantly affect a planet's development and stability by studying various systems. The discovery of water vapor in exoplanet atmospheres is a significant milestone in the field of astronomy, as it opens up new avenues for understanding the potential habitability of these distant worlds. Water is essential for life as we know it, so finding it beyond our solar system suggests that there may be environments where life could exist, or at least where the conditions are suitable for life to develop. When astronomers detect water vapor, they are not just looking for a molecule. They are searching for clues about the atmospheric conditions, the presence of clouds, and even the possibility of liquid water on the surface, which is a key ingredient for life. One of the most notable discoveries was made using the Hubble Space Telescope, which identified water vapor in the atmosphere of the exoplanet HD 1189733, a hot Jupiter located about 64 light-years away from Earth. This finding was groundbreaking because it demonstrated that we could analyze the atmospheres of exoplanets and look for specific molecules that indicate the presence of water. Additionally, the James Webb Space Telescope, which launched in late 2021, has further enhanced our ability to study exoplanet atmospheres in unprecedented detail, promising even more discoveries regarding water and other crucial compounds. The presence of water vapor also provides insight into the formation and evolution of planetary systems. By studying the composition of exoplanet atmospheres, scientists can learn about the processes that shaped these planets, including their distance from their stars, the type of stars they orbit, and the materials available for building planets in their vicinity. This information is vital as it helps us understand how diverse planetary systems can be and whether similar processes could lead to the formation of habitable planets elsewhere in the universe. Moreover, the detection of water vapor can help refine our methods for categorizing exoplanets. For instance, identifying water vapor in a planet's atmosphere might suggest that it falls into a category of potentially habitable planets, which includes those that are in the so-called Goldilocks zone, where conditions are just right, not too hot and not too cold for liquid water to exist. This categorization aids astronomers in prioritizing which exoplanets to study further as they search for signs of life or the conditions that might support it. In conclusion, the significance of discovering water vapor in exoplanet atmospheres cannot be overstated. It not only enhances our understanding of where life could potentially arise in the universe, but also expands our knowledge of the cosmos as a whole. Researchers employ a variety of sophisticated techniques to differentiate between false positives and actual exoplanet signals, which is crucial in the search for planets beyond our solar system. One of the primary methods involves the use of transit photometry, where scientists monitor the brightness of stars over time, looking for periodic dips in brightness, which may indicate a planet passing in front of a star, blocking some of its light. However, these dips can also be caused by other phenomena, such as star spots or eclipsing binaries. To distinguish genuine signals from these false positives, researchers utilize additional observational data, often from multiple wavelengths or even different telescopes. Another important aspect is the analysis of the light curves, which are the graphs showing the brightness of a star over time. By examining the shape, duration, and depth of these dips in brightness, scientists can glean vital information about the potential exoplanet's size, orbital period, and distance from its host star. For instance, if the transit signal is consistent with multiple transits occurring at regular intervals, it strengthens the case that what they are observing is indeed an exoplanet. Furthermore, researchers also look for what is known as transit timing variation, where the timing of the transits can be altered by the gravitational pull of other planets in the system, providing additional evidence to support the existence of the exoplanet. Moreover, spectroscopic analysis plays a key role in confirming exoplanet signals. By studying the spectrum of light emitted by a star, scientists can detect the chemical signatures of an exoplanet's atmosphere during transits. This technique allows researchers to identify elements and molecules, such as water vapor or methane, that may indicate the presence of an actual planet rather than a false positive caused by stellar activity. Additionally, researchers use the radial velocity method, which detects changes in the star's motion due to gravitational interactions with an orbiting planet. This method can confirm the presence of an exoplanet by measuring the wobble of the star caused by the gravitational pull of the planet. When both transit photometry and radial velocity data align, it offers a compelling case for the existence of an exoplanet. To further reduce the chances of false positives, researchers often analyze the statistics of known exoplanets, comparing new findings against established databases. The Kepler Space Telescope, for example, has provided a wealth of data that helps scientists develop statistical models to predict the likelihood that a given signal is genuine. Citizen science, a fascinating and growing field, plays a crucial role in the discovery of exoplanets, which are planets located outside our solar system, often orbiting distant stars. Traditionally, the search for these mysterious worlds has been the domain of professional astronomers, using advanced telescopes and sophisticated technology. But citizen scientists, passionate and curious individuals, have become invaluable contributors to this exciting endeavor. Through various projects, these enthusiastic volunteers analyze vast amounts of data collected from space missions, such as NASA's Kepler and TESS missions, which have been designed explicitly to find exoplanets. In these projects, citizen scientists examine light curves, which are graphical representations of a star's brightness over time, looking for the telltale dips in brightness that occur when a planet transits or passes in front of its host star. This process, known as the transit method, is one of the most effective ways to detect exoplanets. The Kepler Space Telescope, for example, has discovered thousands of exoplanet candidates, many of which have been confirmed with the help of citizen scientists who volunteer their time and skills to sift through the data, looking for these small yet significant changes in brightness. One noteworthy project, called Planet Hunters, invites everyday people to participate in the search for exoplanets by examining light curves and identifying potential transits. This initiative has led to the discovery of several new exoplanets, showcasing how the efforts of citizen scientists can complement the work of professional astronomers. By crowdsourcing the analysis of data, researchers can process information much faster, which is especially important given the massive amounts of data generated by space telescopes. This collaborative approach not only accelerates discoveries, but also enriches the scientific community as it encourages public engagement and interest in space exploration. Moreover, citizen science fosters a sense of community among participants as they share their findings and experiences, often forming online groups and forums to discuss their work and learn from one another. This sense of camaraderie can be incredibly motivating as individuals realize they are part of a larger quest to understand the universe, making contributions that could lead to groundbreaking discoveries. The work of citizen scientists has been recognized in scientific publications, with their names appearing as co-authors on research papers highlighting the significant impact they have on the field. Additionally, the role of citizen science extends beyond the initial discovery of exoplanets. It also includes ongoing monitoring and characterization of these distant worlds. Future missions like Plato, which stands for Planetary Transits and Oscillations of Stars, aim to significantly advance exoplanet detection methods through the use of cutting-edge technology and innovative approaches to observing stars and their planetary systems. Scheduled to launch in the coming years, Plato is designed to focus on a wide range of stars, particularly those that are relatively bright, making it easier to detect the slight dimming that occurs when a planet transits in front of its host star. This transit method is one of the most effective ways to identify exoplanets, as it allows scientists to gather important information about the size, orbital period, and distance of these distant worlds from their stars. One of the key advancements that Plato brings to the table is its ability to monitor a large number of stars simultaneously, with a planned observation of over 1 million stars throughout its mission. This large-scale survey will enable the detection of not only larger exoplanets, but also smaller Earth-sized planets that may reside in their stars' habitable zones where conditions might be right for liquid water and potentially life. Unlike previous missions that had focused primarily on nearby stars, Plato will expand its reach, allowing astronomers to gain insights into planetary systems that are much farther away, increasing the chances of discovering a diverse array of exoplanets. Moreover, Plato's advanced photometric capabilities involve high-precision measurements of stellar brightness, which means that it can detect even the faintest transits caused by smaller planets. This precision is crucial for identifying rocky planets that could support life, as even small variations in brightness can reveal the presence of these worlds. Additionally, Plato will also monitor stellar oscillations, which are essentially vibrations in the stars, to glean more information about their properties. By understanding the stars better, scientists can more accurately determine the characteristics of the planets orbiting them. In addition to directly detecting exoplanets, Plato's data will contribute to a broader understanding of how planetary systems form and evolve. By studying the distribution of planets around various types of stars, researchers hope to uncover patterns that could shed light on the processes that lead to the formation of planetary systems, including our own. This mission is particularly exciting because it aligns with the ongoing quest to find potentially habitable exoplanets, ones that could harbor life as we know it. Furthermore, Plato will operate in a complementary manner with other space telescopes such as the James Webb Space Telescope, which is focused on detailed atmospheric studies of exoplanets. The Galileo effect, named after the famous astronomer Galileo Galilei, plays a significant role in the field of exoplanet detection, particularly through its application in the method known as gravitational microlensing. This effect occurs when a massive object like a star or planet passes in front of a more distant light source, such as another star. The gravity of the foreground object bends and magnifies the light coming from the background star, creating a temporary increase in brightness, which can alert astronomers to the presence of planets around the foreground star. The importance of this phenomenon lies in its ability to reveal planets that are otherwise too faint or distant to be observed directly, providing crucial data on their existence, size, and even distance from their parent stars. One of the most exciting aspects of the Galileo effect is that it allows astronomers to detect exoplanets that are located in regions of the galaxy where traditional methods like the transit method or radial velocity method may not be effective. For instance, microlensing can help identify planets that orbit stars in crowded star fields, where the light from many stars can make it challenging to see individual planets. This method has been particularly successful in searching for planets in the Milky Way, but it also opens the door to studying planets in other galaxies, broadening our understanding of planetary systems across the universe. Moreover, the information gathered from microlensing events can lead to insights about the distribution and composition of exoplanets. By analyzing the light curves graphs showing the brightness of the background star over time, scientists can infer the mass of the lensing object, which helps in determining whether it is a star, a brown dwarf, or even a planet. This knowledge is essential as it helps astronomers understand how common or rare different types of planets might be in our galaxy, contributing to the broader questions about planet formation and the potential for life beyond Earth. In addition, the Galileo effect has prompted the development of various observational campaigns and projects such as the Optical Gravitational Lensing Experiment, or OGLE, and the Microlensing Observations in Astrophysics, or MOA, which have successfully discovered numerous exoplanets through this technique. These projects utilize a network of telescopes to continuously monitor stars and capture microlensing events, demonstrating how collaboration and technological advancements in astronomy can lead to significant discoveries. With ongoing advancements in technology, the future of exoplanet detection through the Galileo effect looks promising. Exoplanet detection methods have undergone significant evolution over the years, adapting to new scientific discoveries and technological advancements, which has allowed astronomers to refine their techniques and improve their understanding of these distant worlds. Initially, astronomers relied heavily on the transit method, where they observed the slight dimming of a star's light as a planet crossed in front of it, blocking some of that light. This method, while effective, had its limitations, particularly in detecting smaller Earth-sized planets, as the signal could be weak and easily overshadowed by other stellar activities. As technology advanced, so did the precision of instruments used in these observations. The development of space telescopes like Kepler and TESS enabled more sensitive measurements, allowing for the detection of smaller planets in habitable zones where conditions might be right for life as we know it. This pursuit led to the discovery of thousands of exoplanets, revealing a diverse range of planetary systems, which in turn challenged our previous understanding of how planets form and evolve. Furthermore, the radial velocity method, which detects the wobble of a star caused by the gravitational pull of an orbiting planet, also adapted to accommodate new scientific insights. With improvements in spectroscopic techniques, astronomers could measure these tiny shifts in a star's spectrum with greater accuracy, identifying not just larger gas giants, but also smaller rocky planets. The combination of these methods, along with the incorporation of machine learning and data analysis techniques, has significantly enhanced the ability to identify and confirm exoplanets. In recent years, the advent of direct imaging techniques has also played a crucial role in exoplanet detection. By using specialized instruments like coronagraphs and star shades, astronomers can block out the light from a star, making it easier to see the faint light reflected from a nearby planet. This method has opened up new possibilities, allowing scientists to study the atmospheres of exoplanets and gather data on their composition, which could provide insights into their potential habitability. Moreover, the discovery of exoplanets has sparked a renewed interest in the study of astrobiology, leading researchers to develop new models to predict the types of planets that might support life. This, in turn, has influenced the design of future missions and the development of new detection techniques as scientists seek to focus on specific types of exoplanets that could be more likely to harbor life. As our understanding of the universe expands, the methods used to detect exoplanets continue to evolve and adapt. The discovery of Earth-like exoplanets in habitable zones carries profound implications for our understanding of life beyond our planet, as well as for the future of human exploration and colonization. When scientists identify exoplanets situated in the so-called Goldilocks zone, where conditions are just right, not too hot and not too cold, allowing for the presence of liquid water, there is an immediate excitement about the potential for these planets to support life. This is significant because for decades, astronomers have sought to answer the age-old question of whether we are alone in the universe. Finding planets that share similarities with Earth expands the horizons of astrobiology, encouraging researchers to explore various possibilities for life forms that might exist under different conditions, perhaps even life that relies on biochemistries different from our own. Moreover, these discoveries challenge our current understanding of the formation and evolution of planetary systems. The presence of multiple Earth-like planets within habitable zones suggests that the conditions for life may be more common than previously thought, prompting scientists to rethink the uniqueness of our own solar system. This realization could lead to a paradigm shift in how we approach the search for extraterrestrial life, fueling interest in missions that seek to study these distant worlds in greater detail. The technological advancements required for such explorations also drive innovation here on Earth, as developments in telescope technology, spacecraft design, and planetary science are all interconnected. Furthermore, the implications of finding potentially habitable exoplanets extend to philosophical, ethical, and societal considerations. The possibility of discovering life or even remnants of past civilizations forces humanity to grapple with profound questions about our place in the universe, the nature of life itself, and our responsibilities as stewards of our own planet. It raises discussions about the ethics of space exploration, resource utilization, and the potential for interstellar colonization, as we consider what it might mean to establish a human presence on another planet. Economically, the pursuit of habitable exoplanets could spur investment in space industries, resulting in advancements that benefit both scientific research and commercial applications. As we gather more data about these distant worlds, the potential for mining resources, creating off-Earth colonies, or even terraforming planets becomes more tangible, capturing the imagination of entrepreneurs and scientists alike. The search for Earth-like planets in habitable zones also influences international collaboration in space exploration. Countries around the world are increasingly pooling their resources and knowledge, working together on missions like the James Webb Space Telescope, which is a testament to our collective curiosity. The discovery of exoplanets, which are planets located outside our solar system, has profoundly changed our understanding of our own solar system. It has opened up new avenues of thought in planetary science, astronomy, and even astrobiology. Before we started identifying these distant worlds, our understanding of what constituted a planetary system was primarily based on the 8 planets we see in our solar system, and that understanding was somewhat limited. The first confirmed exoplanet was discovered in 1992, orbiting a pulsar, and since then, thousands of exoplanets have been catalogued, revealing a stunning variety of planetary systems that challenge our previous notions of how planets form and evolve. One major revelation from the study of exoplanets is the diversity of planetary types, which has led scientists to rethink the classification and characteristics of planets. For instance, we have discovered gas giants orbiting very close to their host stars known as hot Jupiters, which are unlike anything in our own solar system. This finding suggests that planetary migration, where planets move inward or outward after their formation, is a common process, and it raises questions about the dynamics of our own solar system's formation. It has prompted researchers to consider how our solar system fits into the broader context of planetary systems in the galaxy, and whether its layout is typical or unique. Moreover, the discovery of exoplanets has brightened the search for habitable worlds. By analyzing the atmospheres of these distant planets, scientists can look for signs of habitability, such as the presence of water vapor, carbon dioxide, and other molecules that could indicate life. This has led to a more nuanced understanding of where life might arise, and it has expanded our search beyond just Earth-like planets to include a wider range of conditions and environments. For example, the discovery of planets in the habitable zone of their stars, where temperatures are just right for liquid water, has encouraged scientists to consider the possibility of life in very different contexts compared to the conditions we have on Earth. Additionally, exoplanet research has revealed that our solar system might be more special than we thought, while also showing that many solar systems may be similar to ours. The detection of multiple planets orbiting a single star has helped astronomers understand the architecture of planetary systems, including how planets interact with each other and how they can influence each other's orbits. This knowledge has implications for understanding the stability of our own solar system and whether its arrangement of planets is a rare occurrence. In the vast expanse of our universe, exoplanets, which are planets outside our solar system, have captured the imagination of scientists and space enthusiasts alike. Among the thousands of candidates discovered, several stand out as particularly intriguing for future study and exploration. One of the most promising candidates is Proxima Centauri b, located just over 4 light-years away from Earth, orbiting the red dwarf star Proxima Centauri. This exoplanet is situated within the habitable zone where conditions could allow for liquid water to exist, raising questions about its potential to support life. Its proximity makes it a prime target for further investigation, especially with upcoming missions that may focus on its atmosphere. Another fascinating candidate is TRAPPIST-1b, one of the 7 Earth-sized planets in the TRAPPIST-1 system, which is about 40 light-years away. This planet, along with its siblings, is also located in the habitable zone of its star, a cool dwarf star, and the possibility of water on its surface makes it an excellent candidate for astrobiological studies. Its relatively close distance allows for detailed observation using current and future telescopes. Then we have LHS 1140b, a super-Earth located roughly 40 light-years away, which has garnered attention due to its size and the potential to have an atmosphere. This exoplanet orbits a star that is much cooler and dimmer than our Sun, allowing it to be in a stable orbit within the habitable zone. What makes it particularly interesting is the potential for its atmosphere to be studied as it transits across its star, giving astronomers a chance to analyze its composition using transit photometry techniques. Moreover, another exciting candidate is Kepler 186f, which is about 500 light-years from Earth. It was the first Earth-sized planet discovered in the habitable zone of another star, and its size and distance from its star are comparable to Earth's. The discovery of this planet suggests that there could be numerous Earth-like worlds waiting to be found in the cosmos. Additionally, one cannot overlook the fascinating world of K2-18b, which is about 124 light-years away and is classified as a super-Earth. It has captured interest because during observations, water vapor was detected in its atmosphere, suggesting that it might have conditions suitable for life. This discovery opens doors for many questions regarding the composition and potential of such worlds. Variations in stellar activity can significantly influence the detection of exoplanets, creating challenges for astronomers and researchers who are keen to identify and study these distant worlds. Stars like our Sun undergo various forms of activity, including sunspots, solar flares, and magnetic field fluctuations, which can all produce signals that may be misinterpreted as the presence of an orbiting planet. For instance, the light emitted by a star can vary in brightness due to these activities, leading to false positives when using methods like the transit method, where astronomers detect the slight dimming of a star's light as a planet passes in front of it. This variability can obscure genuine planetary signals, making it more difficult to confirm the existence of an exoplanet. Moreover, stellar activity can also introduce noise in the radial velocity method, which measures the wobble of a star caused by the gravitational pull of an orbiting planet. If a star is particularly active, its own movements can mimic the gravitational tug of a planet, causing confusion and potentially leading to incorrect conclusions about the presence or characteristics of an exoplanet. This makes it essential for astronomers to account for stellar activity when analyzing data and to use advanced techniques such as statistical modeling and machine learning algorithms to differentiate between the effects of stellar activity and the signals generated by actual planets. To tackle these challenges, researchers often utilize long-term monitoring of stars to understand their activity patterns. By gathering extensive data over time, astronomers can establish a baseline for a star's typical behavior, which helps in identifying anomalies that might indicate the presence of an exoplanet. Additionally, some studies focus on specific types of stars, such as those that are more stable or less active, as they may yield clearer signals and reduce the complications introduced by stellar activity. Furthermore, the development of space-based telescopes like the Kepler Space Telescope and the Transiting Exoplanet Survey Satellite has enhanced our ability to detect exoplanets by minimizing the interference caused by Earth's atmosphere, which can also contribute to noise in observations. These telescopes have allowed for more precise measurements and have improved our understanding of how stellar activity impacts the detection of exoplanets. As astronomers continue to refine their techniques and gather more data, they are better equipped to distinguish between the natural variability of stars and the signals from orbiting planets. This ongoing research not only helps in the search for new exoplanets, but also deepens our understanding of the stars themselves. Binary star systems, which consist of two stars orbiting around a common center of mass, play a significant role in the search for exoplanets for several reasons. When astronomers look for exoplanets, they often use methods like the transit method or the radial velocity method. In binary systems, the gravitational influence of both stars can create interesting dynamics that researchers can study, enabling them to gain insights into the presence of planets. Since binary stars are relatively common in our galaxy, they provide a unique opportunity to explore how planets form and evolve in different environments, as the gravitational tug-of-war between the two stars can affect the orbits of any potential planets. One of the exciting aspects of binary star systems is how they can impact the habitability of planets. The presence of two stars can create complex climates and day-night cycles on planets that orbit them. For instance, a planet could experience varying amounts of sunlight depending on its position in relation to both stars, which might lead to unique atmospheric conditions. This variability could influence the potential for life-making binary systems, fascinating targets for astrobiological research. Moreover, binary systems can also help us identify exoplanets using the gravitational microlensing technique. When a foreground star passes in front of a more distant star, the gravitational field of the foreground star can bend the light from the distant star, creating a temporary brightening effect. If there's a planet orbiting the foreground star, it can cause additional changes in the light curve, leading astronomers to infer the presence of a planet. This method has been particularly useful in detecting planets around stars that are otherwise difficult to observe directly. The study of binary star systems has also led to discoveries about the potential for planet formation in different environments. In some cases, planets have been found in circumbinary orbits, meaning they orbit around both stars. This discovery challenges previous assumptions about how planets could form and survive in such gravitationally complex systems. These findings push the boundaries of our understanding of planetary systems, suggesting that planets can exist in a variety of conditions even where we once thought they could not. Additionally, binary star systems can assist in determining the mass of exoplanets. By observing the motion of the stars in a binary system, astronomers can calculate their masses with high precision. When a planet orbits one of these stars, the gravitational interaction can provide valuable data that helps estimate the planet's mass as well. This is important for understanding the overall characteristics of a planetary system. The presence of a planet's moons can significantly influence its potential for habitability, creating a fascinating dynamic in the search for life beyond Earth. Moons can affect a planet's climate and environment in various ways, impacting everything from its axial tilt to its atmospheric conditions. For instance, a large moon can help stabilize a planet's axial tilt, which in turn helps regulate the planet's climate over long periods. Earth's moon plays a crucial role in maintaining its relatively stable axial tilt of about 23.5 degrees, which contributes to the seasonal variations we experience. If a planet's axial tilt were to vary wildly, it could lead to extreme temperature fluctuations, making it more difficult for life to thrive. Moreover, moons can also influence tidal forces, which can create dynamic ocean environments on a planet's surface. Tides driven by the gravitational pull of a moon can mix ocean waters, potentially leading to more nutrient-rich environments that could foster life. On Earth, the interaction between the moon and our oceans has created habitats that support diverse ecosystems. This tidal action can also lead to geological activity on the planet, which can further enhance habitability by recycling nutrients and creating a more dynamic environment. Additionally, moons can play a role in protecting their parent planets from impacts. A larger moon can help shield a planet from potential asteroid or comet collisions, which might otherwise create catastrophic conditions for life. The presence of a large moon like Earth's could mean fewer dangerous impacts, allowing life to develop and flourish over billions of years in a more stable environment. Furthermore, moons themselves can be of interest when considering habitability. Some of the largest moons in our solar system, such as Europa and Enceladus, have subsurface oceans beneath their icy crusts where conditions might be suitable for life. These moons show signs of geological activity and the presence of water, which are key components for life as we understand it. The interaction between a moon and its planet can lead to interesting chemical processes that might support life either on the moon itself or on the planet. In conclusion, the interplay between a planet and its moons can greatly enhance or diminish the potential for habitability. The stabilizing effects on climate, the influence on tidal forces, the protection from impacts, and the potential for life on the moons themselves all contribute to a complex but essential aspect of planetary habitability. Understanding these dynamics is crucial as we continue to explore our solar system and beyond, searching for places that could harbor life. The search for extraterrestrial life on exoplanets, while exciting and filled with potential discoveries, brings with it a host of ethical considerations that researchers and scientists must carefully navigate. One of the most significant concerns revolves around the potential impact on any extraterrestrial life forms should they exist on these distant worlds. For instance, if we were to discover microbial life on an exoplanet, what responsibilities would we have towards that life? Would it be ethical to study it closely, or even to bring samples back to Earth? This idea relates to the principle of planetary protection, which advocates for the preservation of extraterrestrial environments, ensuring that we do not contaminate them with Earth-based organisms. Moreover, there's the aspect of informed consent, which is a familiar concept in human research, but becomes more complex in the context of non-human life forms. If we were to encounter intelligent extraterrestrial beings, how would we communicate and seek permission to study them or their world? The ethical frameworks that guide human interaction could become inadequate when applied to entirely different life forms, leading to questions about autonomy and respect for their existence. Another important consideration is the potential consequences of contact with extraterrestrial civilizations. The discovery of advanced intelligent life could have profound implications for humanity, raising questions about our place in the universe, the potential for conflict, and the ethical ramifications of sharing knowledge or technology. There's a concern that such interactions might lead to exploitation or harm, whether that be due to misunderstandings, cultural differences, or even the imposition of human values on alien societies. Additionally, the resources and funding allocated to the search for extraterrestrial life must be scrutinized, with pressing issues on Earth such as poverty, climate change, and health crises. Some argue that investing in space exploration diverts attention and resources from solving these critical problems. The ethical dilemma here lies in balancing the pursuit of knowledge about the universe with the responsibility to address the urgent needs of our own planet and its inhabitants. Finally, there's the question of the potential discovery of life on exoplanets and the implication for religious and philosophical beliefs on Earth. Different cultures and religions have varying interpretations of humanity's role in the universe, and the confirmation of extraterrestrial life could challenge or reinforce these beliefs in unexpected ways. This intersection of science, ethics, and faith emphasizes the need for thoughtful discourse as we explore the cosmos. In conclusion, the ethical considerations in the search for extraterrestrial life encompass a wide range of issues, from the potential impact on extraterrestrial life to the allocation of resources and the philosophical implications of such a discovery. Researchers use simulations to predict the characteristics of undiscovered exoplanets by creating detailed mathematical models that mimic the conditions of planetary systems. These models take into account various factors, such as the gravitational forces of nearby stars, the composition of the protoplanetary disk, and the potential influences of other celestial bodies in the vicinity. By adjusting these parameters, scientists can simulate how planets might form, evolve, and interact over time, allowing them to make educated guesses about the characteristics of planets that have yet to be observed directly. One significant approach involves the use of hydrodynamic simulations, which help researchers understand how gas and dust in a protoplanetary disk can come together to form planets. These simulations can illustrate how different conditions like temperature and pressure within the disk influence the size and composition of the resulting planets. For example, a simulation might reveal that in a colder region of the disk, icy bodies can form, leading to the creation of larger gas giants, while in hotter areas, rocky planets are more likely to develop. Another important tool in this research is the statistical analysis of already discovered exoplanets. By examining the known exoplanets' properties, such as their sizes, orbital distances, and compositions, scientists can create statistical models that help predict the likelihood of finding planets with similar characteristics in unexplored regions of space. This method helps narrow down the search for new exoplanets, guiding telescopes to areas where they are more likely to be found. Additionally, researchers employ machine learning techniques to analyze vast data sets from various astronomical surveys. These algorithms can detect patterns and correlations within the data that might be too complex for humans to identify. By training these models on known exoplanet characteristics, researchers can refine their predictions about the types of planets that exist beyond our solar system, even those that may be located in distant star systems. The Kepler Space Telescope, for example, has provided a wealth of data that has significantly impacted our understanding of exoplanet demographics. Researchers have used this data to refine their simulations, comparing predicted outcomes based on different initial conditions with the actual observations made by Kepler. This iterative process of simulation observation and adjustment allows scientists to enhance their models continuously, leading to more accurate predictions about undiscovered planets. Furthermore, researchers simulate the effects of stellar activity, such as flares or radiation emitted by stars, on the potential habitability of exoplanets. These simulations incorporate complex interactions between a star and its planets, assessing how varying levels of stellar activity could impact a planet's atmosphere and surface conditions over time. In recent years, the study of exoplanets, which are planets outside our solar system, has seen a significant boost, largely due to advancements in computational power. These enhancements in technology, specifically in computing capabilities, have allowed scientists to analyze vast amounts of data collected from various astronomical missions, like NASA's Kepler Space Telescope and the Transiting Exoplanet Survey Satellite, or TESS. The sheer volume of data generated from these missions is staggering, with millions of stars monitored for tiny dips in brightness, indicating the presence of a planet passing in front of them. High-performance computing, including the use of supercomputers, has enabled researchers to simulate complex physical processes, such as the atmospheres of these distant worlds. By running intricate models, scientists can predict how light interacts with the atmospheres of exoplanets, helping to deduce their chemical compositions and potential habitability. For instance, breakthroughs in machine learning, a subset of artificial intelligence, have also played a crucial role. These algorithms can sift through extensive data sets far more rapidly than traditional methods, identifying patterns and features that might otherwise go unnoticed. Moreover, advancements in parallel processing allow multiple calculations to be conducted simultaneously, significantly speeding up the analysis of data. This means that scientists can more quickly confirm whether a signal detected in the data truly indicates an exoplanet or if it is a false positive caused by other celestial phenomena. With the power to process and analyze data at unprecedented speeds, researchers are not only identifying new exoplanets, but also characterizing their atmospheres and surface conditions with greater accuracy. In addition, the development of cloud computing has made it easier for astronomers worldwide to share and collaborate on their findings. By utilizing shared resources, researchers can leverage computational power that might be unavailable at their own institutions, leading to a more collaborative environment in the field of exoplanet research. This sharing of resources has also enabled the use of sophisticated data analysis techniques, such as Bayesian inference, which helps scientists make probabilistic statements about the likelihood of exoplanetary characteristics based on the data available. Furthermore, The rise of citizen science initiatives where volunteers help with data analysis has been made possible by advancements in computational power, allowing even non-experts to contribute to the discovery and study of exoplanets. This democratization of science not only increases the manpower available for analyzing data, but also helps engage the public in the excitement of space exploration. As computational power continues to evolve, we can expect even more remarkable discoveries in the field of exoplanet research. Astronomers use a variety of techniques to ensure the reliability of exoplanet detection methods, and this process involves rigorous testing, cross-validation, and an understanding of the limitations of each technique. One of the primary methods for detecting exoplanets is the transit method, where astronomers observe the dimming of a star as a planet passes in front of it, blocking some of the light. To ensure reliability, astronomers look for multiple transits of the same planet, as a single event could be caused by other factors such as star spots or instrumental noise. By confirming that the star dims repeatedly at regular intervals, astronomers can be more confident that they have indeed detected a planet. Another key method is the radial velocity technique, which measures the wobble of a star caused by the gravitational pull of an orbiting planet. To ensure the reliability of this method, astronomers often combine data from multiple observations taken over different times and use sophisticated statistical models to analyze the results. This helps to distinguish between actual planetary signals and false positives that could arise from other stellar phenomena. In addition to these methods, astronomers frequently cross-reference findings with data from other telescopes and missions, such as NASA's Kepler Space Telescope or the Transiting Exoplanet Survey Satellite, known as TESS. This collaborative approach helps to validate discoveries as independent observations can reinforce the evidence for a planet's existence. Furthermore, astronomers use advanced simulation models to understand the characteristics of stars and exoplanets, testing their detection methods against these simulations to evaluate their accuracy. This helps them to identify potential sources of error and refine their techniques. They also consider the statistical significance of their findings, employing techniques like the false positive rate to assess how likely it is that a detected signal is due to chance rather than an actual planet. Additionally, the use of machine learning algorithms has become increasingly important, as these tools can analyze vast amounts of data, identifying patterns that might indicate the presence of exoplanets while filtering out noise from other sources. Peer review and collaboration within the scientific community play a crucial role in validating exoplanet discoveries as astronomers share their findings, methodologies, and data, inviting scrutiny and feedback from others in the field. This collective effort helps to establish a consensus on whether a detection is reliable or if further investigation is needed. Moreover, long-term monitoring of known exoplanets allows astronomers to gather more data, improving their understanding of these distant worlds and confirming their existence through additional observations. International collaboration plays a crucial role in exoplanetary search, as the search for planets beyond our solar system requires a diverse range of expertise, resources, and technologies, which are often found across different countries and institutions. By pooling together their knowledge and capabilities, scientists from various nations can tackle the complex challenges associated with detecting and studying exoplanets, which are often located light years away. For instance, large telescopes like the European Southern Observatory's Very Large Telescope in Chile are often used in tandem with space telescopes such as NASA's Kepler or the Transiting Exoplanet Survey Satellite to gather data on distant worlds. This collaboration allows researchers to share observations, methodologies, and findings, leading to a more comprehensive understanding of planetary systems. Moreover, international partnerships facilitate the sharing of data, which is critical in exoplanet research, where data sets can be vast and complex. Organizations like the International Astronomical Union enable scientists to access a wealth of information, leading to collaborative papers and joint missions that can yield groundbreaking discoveries. For example, the collaboration between NASA and the European Space Agency on missions like the James Webb Space Telescope allows for advanced studies not only in exoplanet characterization, but also in identifying the atmospheric components that might suggest the presence of life. Additionally, international collaboration fosters innovation as diverse teams bring together different perspectives and ideas, which can lead to novel approaches in technology and research methods. The development of advanced instrumentation for detecting exoplanets, such as high-contrast imaging systems, often benefits from the integration of expertise from multiple countries, enhancing the capabilities of researchers to observe faint signals from distant planets against the bright light of their host stars. Furthermore, collaborative efforts can also help in the establishment of global networks for education and outreach, promoting public interest in astronomy and space science. By engaging students and the public through joint educational programs, institutions across borders can inspire the next generation of scientists who will continue the important work of exploring the universe. These partnerships often lead to shared workshops, conferences, and seminars where researchers can exchange ideas and inspire one another. Lastly, as the quest for exoplanets often intersects with questions about habitability and planetary systems, international collaboration is vital in addressing the ethical and philosophical considerations surrounding the search for extraterrestrial life. By working together, scientists can explore the implications of their discoveries in a global context, ensuring that the pursuit of knowledge is conducted responsibly and inclusively. The concept of cosmic inflation is a fascinating and profoundly counterintuitive idea in modern cosmology. It proposes that in the very first, fleeting moments of its existence, our universe underwent a period of astonishing, hyper-accelerated expansion. This is a story that begins not with a slow, gradual unfolding, but with a cataclysmic and almost unimaginable burst of creation. The theory, first introduced in the early 1980s by the physicist Alan Guth, suggests that in a tiny fraction of a second after the Big Bang, a period of time so short it is almost impossible for the human mind to comprehend, the universe expanded at a rate that was vastly faster than the speed of light. This was not a violation of Einstein's theory of relativity, as it was not matter that was moving through space, but space itself that was being stretched, the very fabric of reality being inflated like a cosmic balloon. This brief, but incredibly violent, period of exponential growth is thought to have smoothed out any initial irregularities in the nascent universe, leading to the remarkably uniform and isotropic cosmos that we observe today. The primary evidence for this strange and wonderful idea comes from our detailed studies of the cosmic microwave background, the faint, ancient afterglow of the Big Bang. When we look out at the CMB, we are seeing a baby picture of our universe, a snapshot of the cosmos when it was just 380,000 years old. And what we see is a universe of almost perfect uniformity. A thermal bath with a temperature that is the same in all directions to an accuracy of 1 part in 100,000. But imprinted on this smooth background are tiny, almost imperceptible temperature fluctuations, ripples in the primordial plasma that were the seeds of all future cosmic structure. The statistical properties of these fluctuations, as measured with incredible precision by satellites like the Planck Observatory, are a stunning confirmation of the predictions of the inflationary model. The data reveals a universe that is geometrically flat, a key prediction of inflation, and the specific pattern of the fluctuations provides a direct window into the physics of the universe's first moments, suggesting that the grand macroscopic structure we see today, the vast web of galaxies and clusters, is a fossil, a macroscopic manifestation of the tiny quantum fluctuations that were stretched to astronomical scales during the inflationary epoch. But the theory of inflation does more than just explain the universe we see. It also makes a bold and testable prediction that this period of violent, accelerated expansion should have generated a faint, primordial background of gravitational waves, ripples in the very fabric of space-time. The search for this faint, gravitational whisper from the beginning of time, through experiments like LIGO and future space-based observatories, is one of the great ongoing quests in modern physics. If detected, it would be a definitive, smoking gun confirmation of inflation and a new and incredibly powerful window onto the birth of our universe. The theory of cosmic inflation, in its most basic form, is a story of a single, dramatic event at the dawn of time. But in its more modern and more speculative developments, it has blossomed into a much grander and far stranger vision of reality, the concept of eternal inflation and the multiverse. This idea, pioneered by physicists like Andre Linde and Paul Steinhardt, suggests that the process of inflation, once it begins, may never truly end. Instead, it becomes a self-reproducing, eternal process, a cosmic fractal that is constantly spawning new bubble universes. In this picture, the end of inflation in our own local region of space was just that, a local event. The larger meta-universe, the inflationary sea, is still out there, expanding at an incredible rate, and constantly and randomly, giving rise to new bubbles, new big bangs, new universes. Our entire observable cosmos, with its hundreds of billions of galaxies, is just one tiny, and perhaps insignificant, bubble in an infinite, bubbling foam of other worlds, and these other worlds may not be like our own. The specific way in which the inflationary energy decays in each bubble can lead to different vacuum states, which in turn can result in different fundamental particles, different forces of nature, and different physical laws. There could be universes with more or fewer dimensions of space, universes where gravity is a repulsive force, universes where the chemistry of life is impossible. Most of these universes would be sterile, bizarre, and inhospitable wastelands. But in an infinite multiverse, even the most improbable events become not just possible, but inevitable. The existence of a universe like ours, with its specific and seemingly fine-tuned set of physical constants that allow for the formation of stars, planets, and conscious observers, is no longer a miracle that requires a special and perhaps supernatural explanation. It becomes a simple and almost mundane selection effect. We find ourselves in a universe that is hospitable to life for the same reason that we find ourselves living on a planet that is not too close and not too far from its star. It is the only kind of place where beings like us could evolve to ask the question. The multiverse, in this sense, provides a scientific, albeit untestable, framework for the anthropic principle. This is a vision of reality that is almost impossible to fully comprehend, a vision that pushes the boundaries of our imagination and our very definition of what the universe is. It is a vision that is deeply unsettling to some, as it seems to remove any sense of specialness or purpose from our own cosmic home. But it is a vision that is also, for others, a source of profound wonder and liberation. A vision of a cosmos that is infinitely more creative, more diverse, and more magnificent than we ever dared to imagine. The development of the theory of cosmic inflation is a beautiful case study in the process of scientific discovery. It was not a theory that was born in a single eureka moment, but was the result of a long and often difficult process of grappling with the deep conceptual puzzles that the standard Big Bang model had left unanswered. The theory's primary architect, Alan Guth, was not a seasoned cosmologist when he had his breakthrough insight in 1980. He was a young particle physicist who was trying to understand the implications of grand unified theories, the ambitious and as yet unproven theories that attempt to unify the three non-gravitational forces of nature into a single underlying force at very high energies. These theories predicted that the early universe should have gone through a series of phase transitions, similar to the way that water freezes into ice. And they also predicted the existence of a number of exotic and unwanted relics from these transitions, like magnetic monopoles, that should have been produced in vast numbers and that we do not observe today. It was in the process of trying to solve this monopole problem that Guth stumbled upon the idea of inflation. He realized that a brief period of exponential expansion, driven by the energy of a false vacuum state associated with the gut phase transition, could not only solve the monopole problem, but could also, as a kind of wonderful and initially unintended side effect, solve the horizon and flatness problems as well. Guth's initial model, however, had a fatal flaw. It did not have a graceful exit from the inflationary phase. His universe was full of colliding bubbles that would never coalesce into a smooth, homogeneous cosmos like our own. It was other physicists, like André Linde and Paul Steinhardt, who, in the years that followed, developed the more sophisticated new inflation and chaotic inflation models, which provided a more plausible and elegant mechanism for ending the inflationary phase and for transitioning into the hot Big Bang. This story is a testament to the fact that scientific progress is often not a linear path, but a messy, collaborative, and iterative process. A process of bold conjecture, of rigorous critique, and of collective, creative problem-solving. It is a story that also highlights the deep and fruitful interplay between different fields of physics. The solution to a deep puzzle in cosmology, the puzzle of the universe's initial conditions, came not from a cosmologist, but from a particle physicist who was working on a seemingly unrelated problem. It is a beautiful example of how the search for a deeper understanding of the very small, the world of quantum fields and fundamental particles, can lead to a revolutionary new understanding of the very large, the world of galaxies and the expanding cosmos. The theory of cosmic inflation is now a cornerstone of modern cosmology, a standard and essential part of our story of the universe. But it is a theory that is still, in many ways, a work in progress. We do not yet know the precise identity of the inflaton field or the exact details of its potential energy landscape, and we are still searching for the smoking gun observational evidence, the primordial gravitational waves that would be a definitive confirmation of the theory. The story of inflation is a story that is still being written, and it is a story that is a beautiful and powerful testament to the restless, creative, and endlessly curious nature of the human mind itself. The theory of cosmic inflation is not just a beautiful and elegant idea, it is a powerful scientific theory that makes a number of specific, testable predictions. And in the 4 decades since it was first proposed, it has passed a remarkable series of observational tests, moving it from the realm of speculative conjecture to its current status as the standard and most well-supported paradigm for the origin of our universe. The most important and most precise of these tests has come from our detailed observations of the cosmic microwave background. The CMB, as we have seen, is a snapshot of the universe when it was just 380,000 years old. And the tiny temperature fluctuations in this ancient light are a direct fossil of the primordial density variations that were seeded by inflation. Inflationary theory makes a number of very specific predictions about the statistical properties of these fluctuations. It predicts that the universe should be geometrically flat, which means that the angular size of the fluctuations on the CMB sky should have a very specific characteristic scale. It predicts that the fluctuations should be Gaussian, meaning they should have a random, bell curve-like distribution. And it predicts that the power spectrum of the fluctuations, a measure of how their amplitude changes with angular scale, should be nearly, but not quite, scale invariant. This means that the fluctuations should have roughly the same strength on all scales, but with a slight red tilt, a slight tendency for the fluctuations to be stronger on larger scales than on smaller ones. The detailed, all-sky maps of the CMB, created by the DAUMAP and Planck satellites, have tested these predictions with stunning precision. And the results have been a triumphant confirmation of the inflationary paradigm, The universe is observed to be flat to within a fraction of a percent. The fluctuations are observed to be almost perfectly Gaussian, and the power spectrum is observed to be almost perfectly scale invariant, with just the slight T-red tilt that the simplest models of inflation predict. This is a remarkable achievement. It is a direct observational link between the largest scale structures in our universe and the quantum fluctuations of a hypothetical field in the first fleeting moments of time. But the ultimate and most sought-after confirmation of inflation would be the detection of a specific and unique signature in the polarization of the cosmic microwave background. Polarization is a property of light that describes the orientation of its electromagnetic waves. The CMB is expected to be polarized. And this polarization can be decomposed into two different patterns, known as E modes and B modes. The density fluctuations seeded by inflation are expected to produce only E-mode polarization. But inflation also predicts the existence of a primordial background of gravitational waves, ripples in the fabric of space-time itself. And these gravitational waves would have left a unique and unmistakable imprint on the CMB, a faint swirling pattern of B-mode polarization. The detection of these primordial B-modes is the holy grail of observational cosmology. It would be a direct and unambiguous confirmation of inflation, and it would also provide us with a direct measurement of the energy scale at which inflation occurred, a glimpse into the physics of the universe at energies that are 1 trillion times higher than anything we can achieve in our terrestrial particle accelerators. In 2014, the BICEP-2 experiment at the South Pole announced that they had detected just such a signal. The announcement was met with a wave of excitement and fanfare, but it was, unfortunately, a false alarm. It was later shown that the signal they had detected was not from primordial gravitational waves, but was due to the polarized emission from dust within our own Milky Way galaxy. The search for the primordial B modes continues, with a new generation of more sensitive, ground-based and balloon-borne experiments. It is a search that is pushing the very limits of our observational capabilities. A search for a signal that is incredibly faint and is hidden behind a complex and confusing veil of galactic foregrounds. But it is a search that is worth the effort, for in that faint, swirling pattern of ancient, polarized light lies the key to one of the deepest and most profound secrets of the cosmos, the story of our own. Inflationary birth. The theory of cosmic inflation, born from the desire to solve the puzzles of the Big Bang, has, in turn, opened up a new and even deeper set of questions about the ultimate nature of our universe. The simple and most successful models of inflation. The slow-roll models are based on the idea of a single, simple inflaton field that slowly rolls down a smooth, potential energy hill. But there is nothing in our fundamental theories that tells us that this must be the case. The landscape of possible quantum fields and their potential energy surfaces is a vast and largely unexplored territory. This has led to the development of a whole zoo of different inflationary models, each with its own unique set of assumptions and predictions. The chaotic inflation model of Andre Linde, for example, proposes that the initial conditions of the universe were not smooth and ordered, but were, as the name suggests, chaotic. The inflaton field could have had different random values in different regions of space. In some regions, the field would have been at the bottom of its potential well and no inflation would have occurred. In other regions, it would have been high up on its potential hill, triggering a period of rapid inflationary expansion. This model leads naturally to the idea of a multiverse, with our own observable universe being just one of a vast number of other causally disconnected regions of space that also underwent inflation. Other models propose a more complex inflationary sector, with multiple interacting inflaton fields. These multi-field or hybrid inflation models can lead to a richer and more complex set of observational predictions. For example, they can produce non-Gaussian fluctuations in the cosmic microwave background, specific, non-random patterns that could be a telltale sign of the interaction between different fields in the early universe. The search for these non-Gaussian signatures is a major goal of the precision cosmology experiments like the Planck satellite. String theory, our most ambitious and mathematically sophisticated attempt at a unified theory of everything, also has its own unique take on inflation. In brain inflation models, the inflationary expansion is driven by the motion of brains, the higher dimensional objects that are a key feature of the theory. Our own three-dimensional universe could be one of these brains, and the period of inflation could correspond to a time when another parallel brain was moving towards our own, with the potential energy between the brains acting as the inflaton. The end of inflation, in this picture, is the cataclysmic and universe-creating collision of the two brains. This is a beautiful and highly speculative idea, and it is one that can also lead to unique and potentially observable signatures, like the production of cosmic strings, one-dimensional defects in space-time that could be detected through their gravitational lensing effects. This proliferation of different inflationary models has been criticized by some as a sign of the theory's weakness. If the theory is so flexible that it can accommodate almost any new observational result, is it truly a predictive scientific theory? This is a valid and important critique, but it is also a sign of the theory's richness and its deep connection to the most fundamental questions of theoretical physics. The period of inflation is a unique and powerful laboratory, a window onto the physics of the universe at energies that are far beyond the reach of any terrestrial experiment. The subtle patterns in the ancient light of the cosmic microwave background are the fossils of this primordial epoch, and by studying them with ever-increasing precision, we are not just testing the general idea of inflation, we are also, in a very real sense, doing experimental particle physics at the highest possible energies. We are probing the nature of the quantum fields that governed the first moments of creation, and we are searching for the subtle clues that will point us towards a deeper, more unified, and more complete understanding of the fundamental laws of nature. The cosmic microwave background radiation is more than just a beautiful baby picture of our universe. It is a rich and detailed scientific document, a Rosetta Stone that has allowed us to decipher the fundamental parameters of our cosmos with an accuracy that was unimaginable just a few decades ago. The CMB is a perfect black-body radiator, and the overall shape of its energy spectrum, as measured with incredible precision by the Kobe satellite in the early 1990s, is a stunning confirmation of the hot Big Bang model. But the true scientific treasure of the CMB lies in its tiny anisotropies, the 1 part in 100,000 temperature fluctuations that are imprinted on this otherwise uniform glow. These fluctuations are a direct fossil of the primordial density variations that were present in the universe when it was just 380,000 years old. And they are the seeds from which all the large-scale structure in our universe, the galaxies, the clusters, the cosmic web has grown, the statistical properties of these fluctuations, and in particular their angular power spectrum, a plot of how their amplitude varies with their size on the sky, is an incredibly powerful cosmological tool. This power spectrum is not a smooth curve. It has a series of characteristic acoustic peaks. These peaks are the frozen signature of sound waves that were propagating through the hot, dense, primordial plasma of the early universe. Before recombination, the universe was a soup of protons, electrons, and photons, all tightly coupled together. A region of slightly higher density, created by the primordial inflationary fluctuations, would have a stronger gravitational pull, and it would begin to collapse. But as it collapsed, The pressure of the trapped photons would push back, causing the region to expand and to rarefy. This would then reduce the photon pressure, allowing gravity to take over again. And the region would begin to collapse once more. This cycle of gravitational collapse and pressure-driven expansion created a series of oscillating sound waves that rippled through the primordial plasma. The acoustic peaks in the CMB power spectrum correspond to the specific, resonant frequencies of these sound waves. The modes that happen to be at their point of maximum compression or maximum rarefaction at the precise moment of recombination, when the universe became transparent and the photons were released. By precisely measuring the positions and the heights of these peaks, we can extract a wealth of information about the fundamental parameters of our universe. The angular scale of the first and largest peak, for example, is a direct measure of the overall geometry of the universe. The fact that this peak is observed at an angular scale of about 1 degree is the primary evidence that our universe is geometrically flat. The relative heights of the odd and the even peaks tell us about the density of baryonic matter in the universe. And the overall shape of the power spectrum, particularly at small angular scales, is a sensitive probe of the amount of dark matter in the universe. The detailed all-sky maps of the CMB, created by the WMAP and the Planck satellites, have allowed us to measure these acoustic peaks with a precision of a few percent, and in doing so, to determine the fundamental parameters of our standard cosmological model, the Lambda CDM model, with an accuracy that is the envy of many other fields of science. We now know, with high confidence, that our universe is about 13.8 billion years old, that it is geometrically flat, and that it is composed of about 5% normal matter, 27% dark matter, and 68% dark energy. This is a monumental achievement, a testament to the power of modern and precision cosmology. And it is a story that is written in the subtle and beautiful language of sound waves, in the faint, ancient, and ever-present light of the cosmic microwave background. The theory of cosmic inflation is not the only idea that has been proposed to explain the origin of the large-scale structure we see in the universe. While it is the leading and most well-supported paradigm, it is not without its challenges and its critics, and this has spurred the development of a number of interesting and often radical alternative theories. One of the most long-standing of these alternatives is the idea of cosmic strings and other topological defects. In this picture, the early universe, as it cooled after the Big Bang, went through a series of phase transitions, similar to the way that water freezes into ice. These phase transitions, which are predicted by many theories of high-energy particle physics, could have left behind a network of defects, like the cracks that can form in a block of ice as it freezes. Cosmic strings are one-dimensional, line-like defects, incredibly thin, but with an immense energy density. In the 1980s, it was thought that these strings, as they whipped through the early universe at nearly the speed of light, could have acted as the gravitational seeds for galaxy formation. This was a very compelling and elegant idea, as it provided a natural link between particle physics and cosmology. However, the detailed observations of the cosmic microwave background from the COBE and WMAP satellites showed a pattern of fluctuations that was not consistent with the predictions of the cosmic string model. The fluctuations were too Gaussian, too random, to have been produced by the sharp linear features of a network of strings. This led most of the cosmological community to abandon the cosmic string model as the primary source of cosmic structure, and to embrace the inflationary paradigm instead. But this does not mean that cosmic strings do not exist. They could still be out there as a subdominant component of the universe, and astronomers are still actively searching for their subtle gravitational lensing signatures. Another, more recent, and more radical alternative to inflation is the ekpyrotic or cyclic universe model, which we have discussed. In this picture, the hot, dense state of the Big Bang is not the beginning of time, but is the result of a collision between two parallel branes in a higher dimensional space. The density fluctuations that seed the formation of galaxies are not generated by the quantum fluctuations of an inflaton field during a period of exponential expansion, but are generated by quantum fluctuations before the brane collision, during a long, slow period of contraction. These fluctuations are then converted into the familiar scale-invariant density perturbations during the collision itself. This is a very different physical mechanism from inflation, and it makes a number of subtly different and potentially testable predictions. For example, the simplest ekpyrotic models predict a complete absence of primordial gravitational waves, a prediction that is in stark contrast to that of many inflationary models. The search for the B-mode polarization in the CMB is, therefore, a crucial test that can distinguish between these two very different pictures of our cosmic origins. A third class of alternatives attempts to solve the puzzles of the Big Bang without invoking any new, high-energy physics in the early universe. These models often involve a modification to the laws of gravity on very large scales, or the existence of a pre-Big Bang phase where the universe was in a different, and perhaps static or contracting, state. These are often more difficult to reconcile with the full range of cosmological data, but they are an important part of the theoretical landscape, a reminder that we should not become too dogmatically attached to a single paradigm. The ongoing dialogue between the standard inflationary model and these alternative theories is a healthy and essential part of the scientific process. It is a dialogue that pushes us to refine our theories, to sharpen our predictions, and to devise new and more powerful observational tests. The universe is a deep and complex place, and it is entirely possible that the true story of our cosmic origins is one that we have not yet even imagined. The search for this story is a grand human adventure, and it is an adventure that is still, in many ways, just beginning. The legacy of the BICEP-2 experiment, with its dramatic announcement of the detection of primordial gravitational waves in 2014, and its subsequent, and equally dramatic, retraction, is a powerful and important story about the nature of the scientific process. It is a story of bold ambition, of incredible technological achievement, of the excitement of a potential paradigm-shifting discovery, and also of the crucial, and sometimes painful, role of scientific skepticism, of peer review, and of the self-correcting nature of science. The BICEP-2 experiment was a specially designed telescope at the South Pole, built for a single, audacious purpose to detect the faint, swirling, B-mode polarization pattern in the cosmic microwave background that would be the smoking gun signature of cosmic inflation. The team, after years of painstaking work and careful analysis, announced that they had detected just such a signal, at a level that was surprisingly strong, but which was consistent with some of the simplest and most elegant models of inflation. The announcement was met with a wave of global excitement. It was hailed as a discovery of Nobel Prize-winning caliber, a direct observational window onto the first, fleeting moments of the universe's existence. But almost immediately, a number of other cosmologists began to raise questions. The signal was very strong, much stronger than many had expected. And there was another, more mundane potential source for a B-mode polarization signal, the emission from interstellar dust within our own Milky Way galaxy. The dust grains in our galaxy are not spherical, and they can be aligned by the galaxy's magnetic field. This means that the thermal, microwave radiation that they emit is partially polarized, and this polarized emission can have a swirling B-mode component. The BICEP-2 team had attempted to account for this dust contamination using the best available models at the time, but the crucial piece of information they were missing was a detailed, all-sky map of the polarized dust emission at their specific observing frequency. And that map was about to be released. by the European Space Agency's Planck satellite. A few months after the BICEP-2 announcement, a joint analysis of the BICEP-2 and the Planck data was published. And the conclusion was unambiguous. The signal that BICEP-2 had detected was not from primordial gravitational waves. It was almost entirely consistent with being from the polarized emission from galactic dust. The dramatic discovery was, in fact, a dramatic mistake. The story of BICEP-2 is not a story of scientific fraud or incompetence. It is a story of a talented and dedicated team of scientists who were pushing the very limits of their instruments, who were working in a new and largely unexplored area of observational cosmology, and who, in their excitement, made a premature and ultimately incorrect interpretation of their data. And it is a story that, in the end, is a beautiful demonstration of how science is supposed to work. The initial claim was met not with blind acceptance, but with a healthy and rigorous skepticism. Other scientists questioned the analysis. They proposed alternative explanations. They demanded more data. And when that new data became available, the original claim was re-evaluated and ultimately corrected. This is the self-correcting nature of science at its very best. And the story is far from over. The BICEP-2 experiment and the controversy that it generated has spurred a new and even more intense global effort to search for the primordial B-modes. A new generation of more sensitive experiments, both at the South Pole and in other parts of the world, are now collecting data, and they are doing so with a much deeper and more sophisticated understanding of the complex, and often confusing, nature of the galactic dust foregrounds. The legacy of BICEP-2 is not one of failure, but one of progress. It was a bold and ultimately unsuccessful first attempt to open a new window onto the cosmos, and in its failure, it has taught us invaluable lessons that will be essential for the ultimate success of this grand and historic quest. The primordial gravitational waves are still out there, waiting to be discovered. And when they are finally and definitively detected, it will be a triumph that is built on the foundations, both the successes and the failures, of the pioneering work of experiments like BICEP-2. The cosmic web, the vast and beautiful large-scale structure of our universe, with its intricate network of filaments, walls, and voids, is the most magnificent and most direct fossil of the inflationary epoch. The theory of cosmic inflation, as we have seen, provides a natural and elegant mechanism for generating the initial primordial density fluctuations that were the seeds of all this structure. In the first, fleeting moments of time, the inherent quantum uncertainty of the inflaton field created a landscape of tiny microscopic ripples in the energy density of the universe. The period of exponential inflationary expansion then took these microscopic quantum ripples and stretched them to astronomical proportions, imprinting them onto the very fabric of space-time. When the inflationary phase ended, these energy fluctuations were converted into density fluctuations in the hot primordial soup of matter and radiation. These were the seeds of creation. The regions of slightly higher density had a slightly stronger gravitational pull, and they began, over the vast sweep of cosmic time, to attract the matter from their surroundings. The regions of slightly lower density, on the other hand, were gradually evacuated, their matter flowing towards the growing high-density regions. This is the process of gravitational instability, the simple and powerful mechanism by which a nearly uniform or primordial universe can, over billions of years, evolve into the rich and complex tapestry of structures that we see today. The dark matter, with its mysterious non-interacting nature, played a crucial and leading role in this process. The normal, baryonic matter of the early universe was tightly coupled to the photons of the cosmic microwave background, and the intense pressure of this radiation prevented it from collapsing under gravity. But the dark matter, which does not interact with light, felt no such pressure. It was free to begin collapsing into the primordial density wells as soon as the universe became matter-dominated. It formed the invisible gravitational scaffolding, the deep dark matter halos into which the normal baryonic gas would later fall, cool, and form the first stars and galaxies. The large-scale structure of the cosmic web is, in this sense, a direct map of the underlying invisible distribution of dark matter. The bright filaments of galaxies are simply the places where the density of dark matter is highest. The vast dark voids are the places where it is lowest. The statistical properties of this cosmic web, the size of the voids, the thickness of the filaments, the clustering of the galaxies are all a direct and predictable consequence of the statistical properties of the primordial inflationary fluctuations. And the agreement between the predictions of the inflationary model and the detailed three-dimensional maps of the universe that we have now created through vast galaxy redshift surveys like the Sloan Digital Sky Survey is another one of the great triumphs of modern cosmology. We can now, with the aid of powerful supercomputer simulations, take the initial conditions as measured in the cosmic microwave background, the baby picture of the universe at 380,000 years old, and we can evolve that universe forward in time, using only the known laws of gravity and physics, and we can produce a simulated universe that looks, in a statistical sense, almost identical to the real universe we observe around us. This is a monumental achievement. It is a direct and unbroken chain of understanding that connects the quantum fluctuations of the first infinitesimal fraction of a second of the universe's existence to the formation of our own Milky Way galaxy. Some 10 billion years later, it is a story of incredible scope, of beautiful coherence, and of profound explanatory power. And it is a story that tells us that we are not just living in the universe. We are a part of its deepest and most ancient structure. The atoms in our bodies, the planet we live on, the galaxy we inhabit, are all the direct and beautiful consequence of the simple and yet profound process of gravitational instability, acting on the faint, primordial, and quantum mechanical seeds that were planted at the very dawn of time. The concept of the inflationary bubble, the idea that our entire observable universe is just a small, and perhaps insignificant, patch of a much larger, and possibly infinite, cosmic reality, is one of the most profound and mind-altering implications of the theory of cosmic inflation. This idea arises naturally from the dynamics of the inflationary process itself. The period of exponential expansion is so incredibly rapid and so incredibly powerful that it can take a region of space that was initially infinitesimally small and stretch it to a size that is vastly larger than our current observable horizon. This means that the universe that was created in the Big Bang is, in all likelihood, much bigger than the part of it that we can see. The homogeneity and the flatness that we observe within our own local cosmic bubble are not necessarily properties of the entire global universe. They are simply the properties of our own inflated patch. This has a number of fascinating and testable consequences. If our universe is just one inflated bubble, then it is possible that there could be other similar bubbles out there, far beyond our horizon. This is the level Y multiverse, a simple and almost unavoidable consequence of an infinite space and a finite period of inflation. But the concept of the inflationary bubble becomes even more radical in the context of eternal inflation. In this scenario, the process of inflation is a self-reproducing one, with new bubble universes constantly being born from the eternally inflating quantum vacuum. Our own inflationary bubble is just one of an infinite number of other bubbles in a vast cosmic multiverse. And these other bubbles may not be like our own. They could have different physical laws, different constants of nature, different numbers of dimensions. This is a vision of reality that is almost impossibly vast and diverse. And it is a vision that provides a potential and deeply compelling explanation for the apparent fine-tuning of our own universe. But the inflationary bubble is not just a concept that is relevant to the very large scales of the cosmos. It also has a profound connection to the very small scales of quantum mechanics. The primordial density fluctuations that were the seeds of all cosmic structure are in this picture. The quantum fluctuations of the inflaton field, frozen into the fabric of space-time as they were stretched beyond the horizon during the inflationary expansion. These fluctuations are, in a sense, a direct macroscopic manifestation of the inherent uncertainty of the quantum world. The specific pattern of hot and cold spots that we see in the cosmic microwave background is the result of a single, specific and random realization of this quantum process. In a different inflationary bubble, the specific pattern of these quantum fluctuations would be different, leading to a different, specific arrangement of galaxies and clusters. This is a deep and beautiful connection. It tells us that the very structure of our universe, the placement of the galaxies, the shape of the cosmic web, is a fossil, a relic of a single, cosmic-scale quantum measurement that took place in the first moments of time. The inflationary bubble is a concept that bridges the gap between the quantum and the cosmos, between the probabilistic world of the very small and the grand, deterministic-looking evolution of the very large. It is a concept that is at the very heart of our modern scientific creation story, a story that is as profound, as beautiful, and as mysterious as any of the ancient myths that it has replaced. The theory of cosmic inflation is not just a story about the past, it is also a story about the future. The same fundamental physics that governed the first and fleeting moments of the universe's existence may also be the key to understanding its ultimate, and perhaps eternal, destiny. The connection between inflation and the future of the cosmos lies in the mysterious and powerful nature of dark energy, the enigmatic force that is currently driving the accelerated expansion of our universe. As we have seen, the leading and most natural candidate for dark energy is the energy of the quantum vacuum itself. And the energy of the quantum vacuum is also the leading and most natural candidate for the energy that drove the period of cosmic inflation. It is a tantalizing and beautiful idea that the same fundamental form of energy is responsible for both the primordial, inflationary burst that created our universe and the gentle, but inexorable, cosmic acceleration that is shaping its future. In this picture, our universe has had two distinct periods of accelerated expansion. The first, inflation, was an incredibly brief but incredibly violent period, driven by the very high energy density of a false vacuum state. The second, the current era of dark energy domination, is a much more gentle and much more long-lived period, driven by the much lower energy density of our current true vacuum state. This raises a profound and difficult question: why are these two energy scales so vastly different? The energy density of the inflationary vacuum was at least 60 orders of magnitude larger than the energy density of the dark energy vacuum we observe today. This is another, and perhaps even deeper, version of the fine-tuning problem. Why did the universe, after its period of high-energy inflation, settle into a vacuum state with an energy that is so incredibly, exquisitely small, but not quite zero? A zero vacuum energy would have led to a universe whose expansion was constantly decelerating under the pull of gravity. A slightly larger vacuum energy would have been so powerful that it would have prevented the formation of galaxies and stars. We live in a universe that seems to be balanced on a razor's edge. the theory of eternal inflation and the multiverse, combined with the string theory landscape of 10 to the power of 500 possible vacuum states, provides a potential anthropic explanation for this. Perhaps all of these different vacuum energies are realized in different bubble universes. We simply find ourselves in one of the rare bubbles where the final dark energy vacuum is small enough to allow for a long and interesting cosmic history. But the connection between inflation and dark energy also opens up other, more speculative and more dramatic possibilities for our cosmic future. What if our current vacuum state is not the true final ground state of the universe? What if it is, like the inflationary vacuum of the early universe, a false vacuum, a metastable state that could, one day, decay into an even lower energy state? This is the scenario of vacuum decay. If a bubble of this true vacuum were to spontaneously nucleate somewhere in our universe, it would expand at nearly the speed of light, converting our familiar vacuum into this new and potentially lethal state as it went. The laws of physics, the properties of the particles, the very stability of matter itself could be different inside this bubble. It would be the ultimate and most final of all cosmic disasters, a phase transition that would literally erase our universe from existence. This is a terrifying but physically plausible possibility. And it is a possibility that is deeply connected to the physics of inflation. The same quantum tunneling processes that may have allowed our universe to begin in a false vacuum state could also, one day, bring it to an end. The story of inflation, then, is a story that is not just about our ultimate origins, but also about our ultimate fate. It is a story that is written in the subtle and still mysterious properties of the quantum vacuum. A story that reminds us that we live in a universe that is not just expanding, but is also, in the deepest sense, a work in progress, a dynamic, evolving, and perhaps, ultimately, an unstable cosmic experiment. The esotropy of our universe, the fact that it looks the same in all directions on large scales, is one of the most fundamental and most well-established of all cosmological observations. It is a cornerstone of the cosmological principle, the idea that we do not occupy a special or privileged position in the cosmos, and it is a property that is beautifully and naturally explained by the theory of cosmic inflation. The inflationary paradigm, with its period of hyper-accelerated expansion, takes a tiny, causally connected, and therefore smooth and isotropic, patch of the primordial universe and stretches it to a size that is vastly larger than our current observable horizon. This ensures that the universe we see today, within our own local cosmic bubble, is, for all practical purposes, perfectly isotropic. But what if this isotropy is not perfect? What if there are subtle, and as yet undetected, deviations from this perfect statistical uniformity? The search for these anisotropies is one of the most exciting and promising frontiers in modern observational cosmology. And it is a search that could provide us with a new and incredibly powerful window onto the physics of the very early universe, and even, perhaps, with the first tantalizing hints of a reality that lies beyond our own. Single universe. Some of the more complex models of inflation, for example, predict the existence of subtle and specific forms of statistical anisotropy in the cosmic microwave background. A model with two or more interacting inflaton fields, for example, could leave a faint but detectable imprint on the CMB, a slight preference for fluctuations of a certain shape or orientation. The search for these non-Gaussian signatures in the high-precision maps of the CMB from the Planck satellite is an active and ongoing area of research. A confirmed detection of non-Gaussianity would be a revolutionary discovery. It would rule out the simplest single-field models of inflation and would provide us with a direct observational probe of the complex. Multi-field dynamics of the primordial universe, another and even more spectacular. Potential source of anisotropy would be a collision with another bubble universe in the context of the multiverse. If our own inflationary bubble had, in its distant past, collided with another, it would have left a cosmic bruise on our sky, a large, circular region of the CMB with a slightly different temperature or polarization. The search for these bubble collision signatures is a high-risk, high-reward endeavor. A confirmed detection would be the first, direct, and unambiguous evidence for the existence of the multiverse, a discovery that would forever change our understanding of our place in the cosmos. Even in the absence of such dramatic primordial signatures, the large-scale structure of the universe that we see today is not perfectly isotropic. The cosmic web, with its filaments and voids, is a testament to this. And on the very largest observable scales, there are some intriguing, and as yet unexplained, hints of a large-scale flow or tilt in the universe, a slight preference for the motion of galaxy clusters in a particular direction. A dark flow. This could be a statistical fluke, a result of the fact that we are only seeing a small and perhaps unrepresentative patch of a much larger and truly isotropic universe. But it could also be a sign of something much deeper, the gravitational influence of a vast, and as yet unseen, concentration of mass that lies beyond our cosmic horizon, a remnant of a large-scale anisotropy in the primordial, inflationary field. The quest to understand the isotropy of our universe and the subtle and potentially profound deviations from it is a quest that is pushing the very limits of our observational capabilities and our theoretical imagination. It is a quest that reminds us that even the most well-established of our scientific principles should be constantly tested, questioned, and probed. For it is often in the small and seemingly insignificant cracks in the facade of our established theories that the first, faint light of a new and more complete understanding of the universe begins to shine. The scientific journey to understand our cosmic origins is a story of a constant and creative dialogue between theory and observation. A bold new theoretical idea, like cosmic inflation, makes a set of specific, testable predictions. A new generation of powerful observational instruments is then built to test these predictions with ever-increasing precision. The results of these observations can either confirm the theory, forcing us to refine and to deepen it, or they can falsify it, sending the theorists back to their blackboards to search for a new and better idea. This is the beautiful, self-correcting, and endlessly progressive nature of the scientific method. And in the field of cosmology, this dialogue is currently playing out in a number of exciting and crucial arenas. The search for the primordial. B-mode polarization in the cosmic microwave background is perhaps the most important and most direct of these tests. A definitive detection of this faint, swirling signal would be a triumphant confirmation of the inflationary paradigm and a direct window onto the physics of the universe's first moments. But a definitive non-detection, Tioen, would be just as profound. If, after a new generation of even more sensitive experiments, we still see no sign of these primordial gravitational waves, it would place incredibly tight constraints on a large class of inflationary models, and it might even force us to abandon the simplest single-field models altogether, pushing us towards more exotic alternatives, like the ekpyrotic or the cyclic universe models, which predict a complete absence of these waves. The precise measurement of the statistical properties of the density fluctuations in the CMB and in the large-scale structure of galaxies is another crucial testing ground. The simplest models of inflation predict a power spectrum of fluctuations that is almost, but not quite, scale invariant, and that is almost, but not quite, perfectly Gaussian. The search for tiny deviations from this simple, vanilla picture, a running of the spectral index, A hint of non-Gaussianity, a subtle statistical anisotropy, is a major focus of modern precision cosmology. Any confirmed detection of such a deviation would be a revolutionary discovery, a direct clue to the more complex and more interesting physics that was at play during the inflationary epoch. Computer simulations are another essential tool in this dialogue between theory and observation. A modern cosmological simulation is a universe in a box, a vast computational experiment that allows us to take the initial conditions as predicted by a particular inflationary model and to evolve them forward in time, using the known laws of gravity and physics to see what kind of universe they produce. We can then compare the statistical properties of this simulated universe, the properties of its galaxies, its clusters, its cosmic web, with the properties of the real universe we observe. This allows us to rule out certain models, to refine others, and to gain a deeper, more intuitive understanding of the complex, nonlinear processes that connect the simple, primordial universe with the rich and complex cosmos we see today. And finally, there is the ever-present possibility of a complete surprise, of a black swan discovery that comes out of left field and forces us to rethink everything. The discovery of dark energy was just such a surprise, and there may be others lurking in the vast and still largely unexplored data sets from our new generation of telescopes. Perhaps we will find a new, unexpected particle in the data from the Large Hadron Collider. Perhaps we will find a fundamental inconsistency in the laws of gravity by observing the motions of stars around the supermassive black hole at the center of our galaxy. The history of science is a history of such surprises, and it is a history that is far from over. The dialogue between theory and observation, between our creative, imaginative models of the universe and the hard, empirical, and often surprising facts that the universe reveals to us, is a dialogue that is at the very heart of the scientific enterprise. It is a dialogue that has, in the last century, given us a story of our cosmic origins that is more profound, more beautiful, and more wondrous than any of our ancient myths. And it is a dialogue that is poised, in the coming years and decades, to lead us to an even deeper and more complete understanding of our place in the grand and ever-unfolding cosmic story. The future of our quest to understand the universe and our own inflationary origins is a future that is bright with the promise of new and even more powerful observational tools. We are living in a golden age of cosmology, an age where our technological capabilities are, for the first time, beginning to match the scale of our deepest and most ambitious scientific questions. In the coming decade, a new generation of ground-based and space-based observatories will come online, and they will provide us with a flood of new, high-precision data that will allow us to test the theory of cosmic inflation and its alternatives with an unprecedented level of rigor. The search for the primordial, B-mode polarization in the cosmic microwave background will be a major focus of this effort. A new Stage 4 CMB experiment, a vast array of telescopes at the South Pole and in the high Atacama Desert of Chile, will map the polarization of the CMB with a sensitivity that is an order of magnitude greater than any previous experiment. This may be our best, and perhaps our final, chance to detect the faint, swirling signature of the gravitational waves from the very beginning of time. In space, the European Space Agency's Euclid mission and the Vera C. Rubin Observatory in Chile will create the largest and most detailed three-dimensional maps of the universe ever made. By measuring the positions and the shapes of billions of galaxies, these surveys will allow us to trace the growth of cosmic structure over the last 10 billion years of cosmic history. This will provide a powerful and completely independent test of the inflationary paradigm. We will be able to compare the statistical properties of the final cosmic web with the statistical properties of the initial seeds as seen in the CMB, a direct and powerful test of our entire gravitational instability model of structure formation. The detection of gravitational waves from other astrophysical sources is also opening a new and revolutionary window onto the cosmos. The current ground-based network of LIGO and Virgo detectors is constantly being upgraded, increasing its sensitivity and its reach. And in the 2030s, the Laser Interferometer Space Antenna will take this new science into space. LISA will be sensitive to the much lower frequency gravitational waves that are emitted by the mergers of supermassive black holes in the centers of distant galaxies. And it may also have the sensitivity to detect the faint, stochastic hum of the gravitational wave background from the Big Bang itself, a direct and pristine signal from the very first moments of the universe's existence. The James Webb Space Telescope will continue to push our observational frontier ever closer to the beginning of time, searching for the very first galaxies to light up the cosmos. And a new generation of powerful, ground-based, 30-meter class telescopes will provide the crucial high-resolution spectroscopic follow-up that will be needed to understand the physics of these first luminous objects. On the theoretical front, the quest for a unified theory of quantum gravity will continue, guided and constrained by these new, high-precision observational data. And the rapid development of quantum computers may one day provide us with a completely new tool for exploring the mysteries of the early universe. A tool that will allow us to simulate the complex quantum dynamics of space-time itself, a simulation that is far beyond the reach of any classical computer. The future of cosmology is a future of synergy, of integration, of a multi-messenger approach that will combine the information from all of these different windows onto the cosmos, the light, the gravitational waves, the neutrinos to create a single, coherent, and deeply nuanced picture of our universe, from its first inflationary moments to its ultimate, and still mysterious, fate. We are living in a remarkable and privileged time, a time when the deepest and most ancient of all human questions, the questions of our own cosmic origins, are finally beginning to come within the reach of our scientific understanding. The journey is far from over, but the path ahead is bright with the promise of discovery. The ultimate fate of our universe, the final chapter in the grand cosmic story, is a topic that has long been a source of fascination, of speculation, and of a certain existential awe. And it is a topic that is intimately and inextricably linked to the physics of the very early universe, to the process of cosmic inflation, and to the mysterious and powerful nature of dark energy. The standard and most plausible scenario for our cosmic future, based on our current best understanding of the data, is that of a big freeze or a heat death. In this picture, the dark energy that is driving the accelerated expansion of the universe is a cosmological constant, an intrinsic and unchanging energy of the vacuum itself. If this is the case, then the universe will continue to expand at an ever-increasing rate, forever. The consequences of this eternal expansion are profound, and ultimately bleak. As the universe expands, the density of matter and radiation will continue to decrease, while the density of dark energy remains constant. This means that dark energy will become more and more dominant over time. The galaxies in our own local gravitationally bound supercluster will eventually merge into a single, vast supergalaxy. But all the other galaxies in the universe will recede from us at an ever-increasing speed, eventually crossing our event horizon and disappearing from our view. The night sky of the far future will be a dark, empty, and lonely place. Within our own isolated supergalaxy, The process of star formation will gradually come to a halt, as the reservoirs of cold, dense gas are used up. The existing stars will one by one exhaust their nuclear fuel, the smaller, sun-like stars fading into cold, dark white dwarfs, and the more massive stars collapsing into neutron stars or black holes. The universe will become a graveyard of stellar remnants. Over much, much longer timescales, even these remnants will begin to decay. The white dwarfs and neutron stars will slowly evaporate through a process of proton decay. If such a process is allowed by a grand unified theory, and the black holes, the most stable of all objects, will slowly but inexorably evaporate through the process of Hawking radiation. After an almost unimaginable amount of time, a googol years or more, the universe will be a cold, dark, and almost perfectly empty void, a thin, featureless soup of photons, neutrinos, and a few stray elementary particles, a state of maximum entropy, a state of final and eternal heat, death. This is a cold and sobering vision of our ultimate cosmic destiny. But it is not the only possibility. If the dark energy is not a cosmological constant, but a more dynamic quintessence field, then its properties could change over time. It is possible that the quintessence field could, in the far future, decay, causing the cosmic acceleration to slow down, to stop, and perhaps even to reverse, leading to a big crunch, a final, fiery collapse of the universe back into a singularity. Or, in a more exotic and more terrifying scenario, the dark energy could be a form of phantom energy, a field whose energy density increases as the universe expands. This would lead to a big rip. In the final moments of such a universe, the repulsive force of the phantom energy would become so strong that it would overcome all the other forces of nature. It would tear apart the galaxy clusters, then the galaxies, then the solar systems, then the planets, and in the final, fleeting instant, it would even tear apart the atoms and the atomic nuclei themselves, ripping the very fabric of space-time into an infinite number of causally disconnected pieces. The physics of cosmic inflation is deeply connected to all of these future scenarios. The specific model of inflation that describes our own early universe determines the initial conditions from which the rest of cosmic history unfolds, and the nature of the inflaton field itself may be a clue to the nature of the dark energy field that is shaping our future. It is a beautiful and deeply profound symmetry that the same fundamental physics that governed the first fleeting moments of our universe's birth may also be the physics that will dictate its ultimate, and perhaps eternal, fate. The relationship between the theory of cosmic inflation and the grand philosophical questions of our origins, our purpose, and our ultimate destiny is a deep and multifaceted one. Inflation is not just a scientific theory. It is a new and profoundly humbling creation story for a modern scientific age. It is a story that has, in many ways, replaced the older, more anthropocentric stories of our religious and mythological traditions. But it is a story that is no less wondrous, no less beautiful, and no less capable of inspiring a sense of awe and reverence for the cosmos. The inflationary paradigm, with its vision of a universe born from a tiny quantum fluctuation in a primordial vacuum, is a story that places our own to human existence in a new and radically different cosmic perspective. It tells us that we are the children of chance, the fortunate and perhaps improbable outcome of a random quantum process at the beginning of time. This is a vision that can be seen as profoundly disenchanting by some, as it seems to remove any sense of a preordained purpose or a divine plan from the cosmos. But it can also be seen as profoundly liberating. If our existence is not the fulfillment of some external purpose, then we are free to create our own meaning, to define our own values, to write our own human story on the vast and otherwise silent canvas of the cosmos. The theory of eternal inflation and the multiverse that it implies takes this sense of cosmic contingency to its ultimate conclusion. If our universe is just one of an infinite number of other parallel realities, each with its own different physical laws, then our own local cosmic home is not just an accident. It is an accident of an almost unimaginable scale. And yet, this vision of a vast and perhaps infinitely diverse multiverse can also be a source of a new kind of cosmic connection, a new kind of cosmic pluralism. It suggests that the principles of creativity, of complexity, of emergence are not unique to our own universe, but are likely to be a common and perhaps universal feature of reality. It invites us to see our own human story not as the only story, but as one of many, a single, beautiful note in an infinite and eternal cosmic symphony. The theory of inflation is also a story about the deep and beautiful connection between the very small and the very large. It tells us that the grand macroscopic structure of our universe, the galaxies, the clusters, the cosmic web, is a direct and fossilized imprint of the quantum fluctuations of the first infinitesimal moments of time. This is a profound and deeply holistic vision of the cosmos. It tells us that the universe is not a collection of separate, disconnected parts, but a single, unified, and co-evolving whole. And we are an integral part of this whole. The atoms in our bodies, the consciousness in our minds, are a direct and unbroken continuation of the same creative process that began in the inflationary fire of the Big Bang. This is a vision of our place in the universe that is not based on a sense of a privileged central position, but on a sense of a deep and deeply humbling participation. We are not the masters of the universe. We are the universe, having become aware of itself. And as we continue to probe the mysteries of our own inflationary origins, with our new and ever more powerful tools of science, we are not just collecting data about the past. We are, in a very real sense, deepening our own self-awareness as a cosmic species. We are piecing together the long, strange, and beautiful story of our own cosmic journey. A journey that has taken us from the quantum foam of the primordial void to the threshold of a new and perhaps boundless future. The future of our quest to understand the universe and our own inflationary origins is a future that is bright with the promise of new and even more powerful observational tools. We are living in a golden age of cosmology, an age where our technological capabilities are, for the first time, beginning to match the scale of our deepest and most ambitious scientific questions. In the coming decade, a new generation of ground-based and space-based observatories will come online, and they will provide us with a flood of new, high-precision data that will allow us to test the theory of cosmic inflation and its alternatives with an unprecedented level of rigor. The search for the primordial. B-mode polarization in the cosmic microwave background will be a major focus of this effort. A new Stage 4 CMB experiment, a vast array of telescopes at the South Pole and in the high Atacama Desert of Chile, will map the polarization of the CMB with a sensitivity that is an order of magnitude greater than any previous experiment. This may be our best, and perhaps our final, chance to detect the faint, swirling signature of the gravitational waves from the very beginning of time. In space, the European Space Agency's Euclid mission and the Vera-C Rubin Observatory in Chile will create the largest and most detailed three-dimensional maps of the universe ever made. By measuring the positions and the shapes of billions of galaxies, these surveys will allow us to trace the growth of cosmic structure over the last 10 billion years of cosmic history. This will provide a powerful and completely independent test of the inflationary paradigm. We will be able to compare the statistical properties of the final cosmic web with the statistical properties of the initial seeds as seen in the CMB, a direct and powerful test of our entire gravitational instability model of structure formation. The detection of gravitational waves from other astrophysical sources is also opening a new and revolutionary window onto the cosmos. The current, ground-based network of LIGO and Virgo detectors is constantly being upgraded, increasing its sensitivity and its reach. And in the 2030s, the Laser Interferometer Space Antenna will take this new science into space. LISA will be sensitive to the much lower frequency gravitational waves that are emitted by the mergers of supermassive black holes in the centers of distant galaxies. And it may also have the sensitivity to detect the faint, stochastic hum of the gravitational wave background from the Big Bang itself, a direct and pristine signal from the very first moments of the universe's existence. The James Webb Space Telescope will continue to push our observational frontier ever closer to the beginning of time, searching for the very first galaxies to light up the cosmos. And a new generation of powerful, ground-based 30-meter class telescopes will provide the crucial high-resolution spectroscopic follow-up that will be needed to understand the physics of these first luminous objects. On the theoretical front, the quest for a unified theory of quantum gravity will continue, guided and constrained by these new high-precision observational data. And the rapid development of quantum computers may one day provide us with a completely new tool for exploring the mysteries of the early universe. A tool that will allow us to simulate the complex quantum dynamics of space-time itself, a simulation that is far beyond the reach of any classical computer. The future of cosmology is a future of synergy, of integration, of a multi-messenger approach that will combine the information from all of these different windows onto the cosmos, the light, the gravitational waves, the neutrinos to create a single, coherent, and deeply nuanced picture of our universe, from its first, inflationary moments to its ultimate, and still mysterious, fate. We are living in a remarkable and privileged time. A time when the deepest and most ancient of all human questions, the questions of our own, cosmic origins are finally beginning to come within the reach of our scientific understanding. The journey is far from over, but the path ahead is bright with the promise of discovery.